How did Dutch engineers build a giant arch full of apartments on top of a swamp?
This one had 3 stories worth of mud, to the point where the workers actually had to wear wetsuits.
What happened when a rock-shaped opera house was built using the most modern and ancient techniques?
Anyone can build a symmetrical auditorium, but here they went weird and wobbly to build something exceptional.
And how was a piece of British history re-engineered for the 21st century?
That is 315 tons of glass and 478 tons of steel.
This is the age of the extraordinary.
This house always is on the verge of falling down.
Where ingenious engineers have unleashed unchecked creativity.
Everything in this building pushes at the boundaries of what's possible.
Building structures so outrageous, they defy logic.
The forces on this thing look like it should be torn apart.
Now, their secrets revealed. Discovering the incredible stories of their construction.
These are extraordinary feats of engineering.
To try and understand, how did they build that? Rotterdam in the Netherlands is one of the biggest ports in the world. Crisscrossed with canals, rivers and docks, water is the lifeblood of this city. However, if you're a builder, this water is much less welcome and something you'd better have a plan for. So when the city wanted to build a massive new horseshoe-shaped structure with 4 floors of underground parking right by the docks, Dutch engineers had to use all the tricks in the book to make it possible.
This building not only has the visible engineering marvel of a huge, unsupported arch, but equally impressive is that they built this into a swamp.
Specialist builders had to dive deep down in a muddy lake to build foundations. Clever concreters created an incredible 12-story high arch, which engineers crowned with extraordinary apartments, apparently built on thin air. These penthouses covered dozens of buzzing market stalls, restaurants and shops. And at each end are the largest cable net windows in Europe. This is Rotterdam's Markthal, or Market Hall. So how did they build it? Following German bombing in World War II, Rotterdam's flattened city centre had been redeveloped, but somehow it had lost its soul.
Rotterdam was planned after the war in a very functional way where they separated living and working and shopping.
And business-like.
Exactly, so they realized, hey, maybe we should combine it because it's not that great to separate.
To liven things up, the city challenged architects to design a permanent covered market with hundreds of new homes either side of it.
So the program demands for 2 slabs of housing and somewhere in between a market hall. I said to them, yeah, but that's boring. So instead of having this with the 2 slabs and then a market hall in between, I said, well, why don't we turn it upside down so that you have slabs on either side and you have more penthouses here and you have a big hall, like a space where you can breathe and where you can monumentalize and good food.
The final approved design was an ingenious merging of housing and markets where not a square centimetre of space was wasted. It would all be built on massive 4-story deep foundations the size of 2 football pitches, dug out of waterlogged ground and waterproofed with concrete. On top, 228 apartments cast in concrete would be stacked like huge bricks, creating the arch walls with a final top floor of penthouses that lock it all together and create the roof. Cladding inside the huge 34-metre-high tunnel would create the largest work of art in the world. Finally, at each end, a grid of cables would support hundreds of panes of glass, protecting the market stalls and cafes inside from the weather.
They've made an entire building in this arched form,
and they've managed to dot apartments and rooms throughout it. It's a really interesting and quite fun piece of engineering.
Building the Markthal would require exceptional engineering skills right from the beginning. The ground is so waterlogged here, anything built below ground level acts like a boat on water.
The basement is actually like a bath at home, and you would take a bucket and try to push the empty bucket into the water. You have to apply a lot of force. And if you push it really down and you let it go, it will jump upwards. And the piles, they have to prevent the basement actually jumping upwards.
To counter this extraordinary upwards force, engineers had to rethink the role of the foundations. Rotterdam is completely waterlogged just 2 meters below the surface. A 4-story deep basement car park the size of 2 football pitches creates vast water pressure underneath it. So long concrete foundation piles would be built down to grip into the soil below, stopping the structure rising. But there's also pressure on the sides. To counter this, a huge concrete grid would be built to hold the walls back. This extreme water pressure and the sheer scale of the building's footprint meant these foundations would be some of the most complex ever built in the Netherlands. Work began in 2009 as the site was cleared and a retaining wall was created using a combination of interlocking steel sheets and tubes hammered in around the edge, making a strong, waterproof perimeter. Then, inside the perimeter, the main foundation piles were made by first driving huge pipes to a depth of 30 meters. An impact hammer slowly but noisily pushed each pile into the soft ground. With over 2,000 piles needed, it was a slow and disruptive process for the locals.
It contains about 2,500 concrete piles to build the foundation, and there was a lot of noise, you know. So they make a wall of, I think it was about 200 containers to reduce the noise. Cracks in the walls, surrounding buildings, so it had a lot of troubles before it got here.
With the pipes hammered the 30 meters down, concrete was poured in to give the building its strong, deep roots. Once set, the tips of these piles were revealed and a massive concrete grid built on top. This will perform a temporary engineering function by bracing the retaining walls against the huge pressure from outside as the engineers dig down a further 11 meters. And this is when building in the Netherlands gets really difficult.
As soon as you dig like 2 meters deep on this location, you will find water. The whole basement with 4 stories underneath the ground level is like building something underwater. It's a kind of underwater building.
As the winter of 2010 progressed, the site became flooded. But instead of being a disaster, it was all part of the plan. The huge grid now underwater was supporting the walls at the top. But as they dug down, the lower part of the walls, which aren't supported, could collapse. This is where the floodwater comes in.
The water inside the basement, it gives a kind of counter pressure. Actually, it gives exactly the same counter pressure as the pressure from the outside.
If the excavators dug down without water inside, pressure from outside would have pushed against the lower dam walls, and eventually the sides would have caved in. The water stopped that, but made for hard work. For months, excavator operators worked blind, only computer screens telling them where to dig. Eventually, all 160,000 cubic meters of material, the equivalent of 64 Olympic swimming pools, had been excavated. Now the engineers had to prepare the bottom of the foundation pit for waterproof concreting, with 15 meters of muddy water still in place. It was time for a very specialized team to get involved.
They continued building, but with builders in wetsuits. This is the most unusual but ingenious method for building foundations.
Highly skilled construction divers swam down to install steel at the bottom of the lake. The piles that formed the foundations needed reinforcing steel attached. This steel would knit together all the piles and the first layer of concrete. Once this was set, it would lock together with the grid above, creating a super strong waterproof box, rigid enough to resist the water pressure from the sides.
Construction workers were putting that reinforcement in place, making the connections between the underwater concrete and the piles, and doing all stuff like that. There were specialized divers which could stay down for a couple of hours and then had to come up again and be refreshed.
Like the excavators, the divers couldn't see what they were doing.
Construction sites are typically dangerous places as it is, let alone this one that had 3 stories worth of a mud pool.
We see very little under the water. A lot of our job is done by feel, so it's basically touch and movement, and generally we have to navigate by it's a mental map in our mind rather than using points of reference.
With the steel reinforcement in position, the next crucial step was to pour the waterproofing concrete so the site could be drained. Extraordinarily, this was achieved by pouring wet concrete into the water.
It might seem surprising, but properly mixed concrete can set just as quickly underwater as it can on land, as long as it's poured gently and it's not agitated during setting. And that's because it's nothing to do with drying. It's actually a chemical reaction that naturally expels water.
For 72 continuous hours, 1,500 loads of waterproof concrete were delivered, laying down a 1.5-meter thick layer to seal the floor of the foundation tank.
After the concrete is set, you can pump out the water. Then you have your empty building pit.
It took 2 weeks to pump out 14 million litres of water. Then the 4 layers of car park floors were poured, and the massively strong 3-dimensional foundation grid was complete. Now the 12-story Markthal could be built. Right at the start, the architects had the vision that a roof for the market would be provided by building a huge arch. An idea that won approval from the structural engineers.
Arches can take many times their own weight, and that's because they use their own weight and gravity as the source of their strength.
Arches are a very efficient structure. They span a gap and they convert whatever load is on that arch into pure compression within the arch and take it down to the ground.
The Romans were already using that. They made concrete and brick arches for bridges and domes. When it's there, it really works well. The trick is how to make it.
Building an arch means creating a curved shape, which is good for strength, but bad when 228 apartments have to fit neatly inside the arch itself. To start with, the engineers took a conventional approach.
In Holland, the construction technique used for apartment buildings is often something called a tunnel form construction technique. It's a set of walls and floors in which you can pour the concrete and thus realize the walls and floors in one go.
Tunnel shuttering uses these large boxes that act as molds, what we call formwork. And these molds, you pour the concrete around. And once the concrete is set, you can just slide these molds out and use them again in another room. So this means that we're saving time, we're saving money, not having to create new pieces of formwork every time.
To speed things up even more, the engineers used technology to keep tabs on exactly when they could move the build forward.
There is a system monitoring the setting of the concrete, And you can read out the results through Wi-Fi or mobile network. So the contractor could see the setting of the concrete from his office and know when he could take the next steps in the construction.
This technology and the repeated shapes of tunnel form construction allowed the floors to be built up super quickly. But how did the engineers make the arch walls curve out and then in as they went up?
We thought of using the apartments as kind of bricks in the arch. Putting the bricks, every step putting the bricks a bit closer, closes the gap already for a large part.
The structural effect of this stepped stacking of apartments is especially plain to see for residents who live higher up in the curve of the arch.
Yeah, you cannot hang stuff in particular maybe on these things. You always have to kind of find a way. So shelves are not really working that well, but pictures still do.
By mid-2013, with the sides of the arch complete, the last apartments to be built would be the exclusive penthouses, forming the flattest part of the arch and the roof of the covered market. Up until now, the build had relied on the apartment below supporting the one on top. But in order to create the arch, engineers had to figure out how to support these penthouses while they built them, 37 meters in the air and over the whole 120-meter length of the hall.
Filling this whole space with a temporary structure would be a project on its own. It would be very costly, it would take a lot of time. So that was the reason to try to eliminate it. So the whole temporary support structure was put on wheels on a crane.
This structure is essentially a reinforced tower set on some tracks. This means that as the roof sections are poured and allowed to set, we can move the structure along the building.
One at a time, floors were craned in and then concrete poured to build up the penthouse structures. When complete, they made up the most crucial engineering blocks in the entire building.
If you have an old-fashioned arch, you will have bricks coming up, and then in the end you have a kind of closing stone filling that gap. The penthouses are actually that kind of closing stone.
Today, the residents of these roof section penthouses enjoy peerless city views and can literally look down on their neighbors.
It's very special because you see all the shops downstairs and you can see the people around you, so yeah, it's nice. Hi there! You see, he likes it.
By early 2014, the project had reached its final stage. Cladding smoothed the outside walls, and the 4,000 aluminium panels inside were each printed with part of a giant mural. The Horn of Plenty was created by Dutch artist Arno Koernen, and at 11,000 square meters, lays claim to being the largest artwork in the world. All that was left to complete this cathedral to food was to weatherproof it with a wall of windows at each end. The designers were determined to retain the openness of an outdoor market and keep the incredible artwork on show from outside. The problem was, Rotterdam's windy weather meant traditional windows this big would need thick frames to remain rigid and prevent the glass from shattering. So the engineers found another, more flexible way.
So it has to be closed, and so no columns. How can I do that? I said, yeah, well, you can make cables.
An array of windows supported by a grid of cables is called a cable net facade. At 630 square meters each, the ones they built here are the biggest in Europe.
The principle of a cable net facade is very similar to a tennis racket, where you have steel cables that are like strings, and then you have glass mounted between them. And this gives the strength, but also the flexibility that's needed for covering an area of this size.
Like the strings on a tennis racket, the cables in the facade must be extremely tight to work. With the 48 cables in place, they were then stretched tight so they could withstand pressure from the wind. Each 3-centimetre thick cable was pre-tensioned by around 30 tons, causing it to lengthen by up to 15 centimetres. Then specialised joints were mounted onto the cable intersections. Here, the glass was clamped on at the corners. These joints, the cables, and the silicon between the glass panels allow for an extraordinary amount of flex in this giant window.
And I'm aware it was quite a work for the engineers to make the joint, because when there is a storm, say wind force 11 or something like that, then it goes in and out for more than a meter.
In December 2014, Markthal's doors were finally thrown open to the public. And they've kept on coming ever since, at a rate of around 20,000 every day.
It's now 5 years old, and the amount of visitors keeps more or less steady around at 8 million, which is actually more than the Eiffel Tower, I can tell you.
By making this multi-purpose market hall possible, its builders have helped start something big in Rotterdam.
It's a real piece of art that they put here together, and we really like it.
It's an amazing piece of construction work. It's also an amazing civic place because it's for everybody.
It may have taken 5 years to rise from the mud, but Markthal now stands as rock-solid evidence of how great engineering and design can be a powerful force for change. "120 kilometers northwest of Hong Kong, in southern China, the brand new megacity of Guangzhou wanted to get noticed. It decided the answer was an incredible new building that would draw the attention of the world. They turned to a legendary architect with a reputation for designing the impossible. Zaha Hadid didn't disappoint. Dreaming up one of the most advanced buildings in the world. Building a gigantic steel frame with techniques that are millennia old. Mimicking natural forms with mathematical wizardry. And redefining the traditional shape of a concert hall that has gone unchallenged for decades.
Anyone can build a symmetrical auditorium, but here they went weird and wobbly to build something exceptional.
This radical design is the Guangzhou Opera House. So how did they build it? The city of Guangzhou is a giant metropolitan center, home to 25 million people, over 3 times the population of New York. In 2002, the regional government commissioned a new centerpiece that would hold its own amongst the city's gleaming skyscrapers. A $200 million opera house. It was designed by the late Zaha Hadid, an architect whose visions pushed at the boundaries of engineering. She found her inspiration just a stone's throw away on the banks of the Pearl River. Simon Yu was the project architect overseeing its construction.
We had this concept of these 2 pebbles by the river, so it's like placed on the river banks, and with the sort of water that sort of washes over it, or these pebbles which are dragged along the sort of the river bank.
The inspiration may have been simple, but it meant creating one of the most advanced buildings in the world.
When you're emulating a natural shape, the first things that go out of the window are symmetry and repetition.
The complex would be made up of 2 auditoriums, a smaller 400-seater, and next door, the larger Opera House, able to seat 1,800 people in its acoustically perfect hall. Both buildings would be cloaked in a net of 12,000 tons of steel frame triangles, joined together by 59 huge, specially designed connectors, creating a strong enough frame for the building's exterior coat. Each is then covered in a jigsaw puzzle of over 75,000 unique hand-cut granite triangles to complete the stunning vision of two pebbles on a riverbank. The engineers started with the simple bit, making the two concrete structures that would house the concert halls. These went up quickly using tried and tested techniques. The first major obstacle came in the form of the giant steel enclosure that wraps the cement structures, a vital part in creating the building's shape.
The Guangzhou Opera House is very clever because it feels like something that's fluid and light, very free-flowing, much like its pebble inspiration. But underneath its curvy skin, it's packing some very, very sophisticated geometry and engineering.
The answer to building the extraordinary 43-meter-tall, 120-meter-wide pebble-shaped shell lay in the humble triangle.
Despite competition from circles, triangles are actually the strongest shape. They're able to distribute the load evenly throughout all three sides. And so because of this, here is really the best shape for evenly distributing the load, carrying it all the way down to the ground of the structure.
To create these triangles, the engineers needed to design and build 59 unique star-shaped joints called knuckles. The incredibly complex design relied on the power of the computer. But for manufacturing them, they turned to an ancient technique called sand casting.
The way they were made was actually quite an old-fashioned way. It was very, very simple in the sense that they actually would make a one-to-one version of these steel members in wood.
To create steel joints using sand casting, the engineers first made the exact shape out of wood. In a foundry, this wooden shape is sandwiched between two layers of sand. The wood is removed, leaving a perfect imprint, creating the mold. Then, molten metal is poured in. It hardens, and when the sand is removed, a steel version of the wooden shape is revealed.
These knuckles were actually all absolutely unique, and they have a very, very tough job of keeping and bracing all these, a lot of the steel together. You know, they all work together.
All the knuckles combine to form the super strong outer shell.
Sand casting, it sounds like really old-fashioned, right? But in this instance, it really is a case of if it ain't broke, don't fix it. The Shang dynasty were using this technique in 1300 BC, and it's still in use today to make one-off pieces.
With the frame in place, the next challenge was creating the pebble-like exterior. The solution lay in yet more triangles, each individually cut to cover the 12,000-ton steel frame. It would be an impressive effect, but an engineering nightmare. To mimic the natural shape of a river-washed pebble, every triangle had to be cut to exact specifications that changed constantly. To make things even harder, the clients loved the idea of the pebble so much, they wanted the building clad in super heavy, super hard granite.
The total granite facade cladding area is 24,700 meters squared, with 75,422 separate pieces. That is essentially the jigsaw puzzle from hell.
The engineers had all 75,000 pieces of stone cut to size off-site. Every tile had a tolerance of 5 millimeters, and lasers were used to make sure each was precisely placed. With the outer shell complete, the engineers turned their laser sights on the sky lobby, an area between the concert halls and the outer shell, where the designers wanted to create a futuristic space with floating walkways with no visible support. The solution hidden inside these impossible balconies are a secret collection of steel boxes, anchored to the building's sturdy concrete core, that support the structures, giving the illusion of weightlessness. They are covered with white organic cladding, created in huge computer-designed molds that were filled with white gypsum plaster and anchored to the steel and concrete frame, piece by piece.
These two separate structures, this self-supporting outer ring and the inner concrete structures, creates this space in the middle that appears to be completely unsupported. And this allowed the architects to play around with these floating staircases and these cantilevered levels that appear to completely defy gravity.
The real challenge, though, lay in creating the concert hall itself. Because to create perfect sound, concert halls are traditionally perfectly symmetrical. This is anything but. The key lay in controlling how the sound bounces around inside the hall.
The art of acoustics is getting the reverberation just right. If there's too little a gap, then everything sounds quite flat. But if there's too long a gap, then you get echoes, and it sounds quite muddy.
They turned to one of the world's leading acoustic engineers to pull it off.
Getting the reflection sequences right, that's the sound that hits the wall or hits the ceiling and ends up at the audience, is vitally important because it adds to the strength of the sound. It can add to the clarity of the sound.
The way you do that is by building what's called a shoebox shape. The sound bounces off the walls and back to the audience. The problem is that the bigger the auditorium, the further the audience is from the stage and the worse the view. But if you fan the audience out, the quality of sound deteriorates. With an 1,800 seat capacity, this space would be huge. So Peter and the team had to find a way to keep the audience close and the sound spot on.
One of the alternatives is asymmetry, where you can use the side walls of the asymmetrical hall to reflect the sound in a way that is similar to a shoebox, that you enforce the lateral reflections.
So the plan was to create curved walls and surfaces within the auditorium to bounce the sound to exactly where the engineers wanted it. But figuring out how to do this was so complicated, Peter and the team decided to build a model of the hall where they could test this out.
In the scale model, you can't test at every seat, but you use dummy heads and microphones to test at a sample, but also you test where you think you're potentially going to have a problem.
By analyzing the sound recorded on the tiny microphones in the different positions, the team were able to build up a picture of exactly how to shape the inside of the hall.
What we were looking for in the model was strong focused reflections from concave surfaces, but also the presence of multiple reflections which will give you the effect of an echo. And such a complex space that this was the only way we felt at that stage we could do it.
By bending and curving the walls, Peter and his team were able to create an amazing sound and not compromise the view. The result of all these complex solutions to engineering problems is a building inspired by nature that is truly out of this world.
This building for me is a perfect example of what happens when architects and engineers and all sorts of other experts work together to challenge the ordinary and the simple.
In the heart of London, engineers and architects faced a problem. How to make a 180-year-old building find its place in the modern world. The solution was a breathtaking revamp, which meant demolishing 2 acres of the old structure and using mathematical precision, replacing it with an 800-ton roof of steel and glass. This is the Great Court of the British Museum. So how did they build it? At the turn of the century, the British Museum was in dire need of modernization. The center of the museum was a cluster of small and confusing rooms, and with nearly 7 million visitors a year struggling to see its 50,000 items, the time had come for change. But transforming a building that's almost 200 years old is a very different proposition from building one from scratch.
Working with an old building can be a nightmare. You never know what you're gonna find or what problems you might run into.
The man tasked with the challenge was one of the world's leading architects responsible for the Millennium Bridge and the Millau Viaduct.
To get from one gallery to another, you'd have to plow through the gallery. So it was a constant traffic jam, and it wasn't very pleasant.
Lord Foster's solution to this maze was to knock it down and create an enormous open space between the exterior facades and circular library in the middle. Over that would go a show-stopping glass roof to create the largest covered square in Europe.
If you then imagine kind of surgically, you take all that stuff around the great circular library, and you've suddenly got breathing space. You've got a vast space. How do you put this glass umbrella so it will evaporate and it's like an artificial sky?
The plan? To demolish the massive rooms filling the area outside the central round library, then to reinforce its foundations, before building a protective shell around the reading room and shore up the exterior walls, ready to receive the 800-ton roof made up of almost 5,000 pieces of steel and over 3,000 panes of glass. No two would be the same. In 1998, with the exhibits moved into storage and the books from the reading room moved to the British Library, work began on demolition and shoring up the 180-year-old foundations.
At the time, the Great Court project was a complete rebuild inside of the courtyard.
Pulling this off, though, was full of risks. They had to strengthen the almost non-existent foundations by pumping concrete 2 stories under the reading room, creating a reinforced slab for it to sit on, and excavating a new basement underneath.
The reading room is a very early, delicate cast iron frame with a very beautiful and listed papier-mâché ceiling. And papier-mâché is dry and very, very delicate, very prone to cracking. So as we dug, you didn't want any movements, or you could easily have cracks appear.
The library sat on shallow foundations that would never take the weight of the roof. So stage 1 was to underpin it by pumping in thousands of tons of concrete. Even this was a delicate operation. Knowing the work could disturb the structure above, alarms were installed. And it turns out, for good reason.
I remember the message coming back, oops, the alarms have gone off. We seem to be lifting the reading room. We'd better stop. And the pumping had got a bit carried away and started moving the reading room upwards.
Can you imagine being the engineers at this point where you've got a precious piece of English history that's stood there for hundreds of years and now it's at risk of being quite seriously damaged?
The next major engineering challenge was that the very delicate central reading room was nowhere near strong enough to carry the weight of the new roof.
In order to keep the heavy weight off the central reading room, we didn't want to load the roof onto the central reading room. So we had put in a ring of columns. They had never got a proper skin on the reading room. It was very ordinary brick. It was never designed to be seen, so it needed a new skin. What Foster's cleverly did was leave a little gap between the new stone and the existing brick. And in that gap, we put 20 new columns and a whole load of cross-bracing to stabilize those 20 columns. And that gave us a beautiful place to take the weight of the roof. And by putting the cross-bracing in it, it also wasn't going to wobble sideways. So it was a really stable core, and nobody even knows it's there. It's all hidden behind the stone.
So, with the foundations in place, the engineers were able to build a hidden steel structure around the central library that would carry the weight of the roof. The library itself would sit safely inside, and then it would all be hidden in the new external finish to the library. Finally, the old building was ready to take the weight of the new glass roof. However, designing a curved glass roof that would join the square outer walls to the circular library was a serious mathematical headache.
I think you have to go and see the roof to kind of understand why it's complicated.
It looks floaty, light, effortless, but that is 315 tons of glass and 478 tons of steel.
The team needed help to realize the design. They turned to computer power.
At a time when we were only just getting used to our computers, really in terms of defining complicated geometries. Now, 20 years on, it's pretty easy, but it wasn't then.
The computer enables you to see the implication of one or several variables, making it possible to create something that is one and the same time extraordinarily complex, but to make it look incredibly simple and, in the end, poetic.
With the geometry of each piece of glass and steel calculated, the engineers got to work transferring it from the computer to the courtyard, starting with building the 2-acre mesh of steel.
So it's a new structure at the circular heart of this. And then all that very delicate tracery of steel members, 11 kilometers in total length, making over 3,300 triangles. And that whole thing can move. It can expand, it can contract, it can absorb snow loads, it can move, and it's only delivering vertical loads onto the historic fabric.
The team then installed the 3,312 panels of glass. With no two pieces the same, it was an enormous jigsaw puzzle to complete.
It's like an iceberg. You're seeing the tip. What you're not seeing is that extraordinary body of work by so many individuals, the people who made it.
Finally, on December the 6th, 2000, the Great Court opened to the public.
It's the largest covered public square in Europe. An incredible piece of engineering.
The new courtyard with its floating glass roof is the result of thousands of man-hours from Lord Foster's team of designers, builders, and engineers. The result is an extraordinary modern structure that has transformed one of London's most important old buildings. How did a team of engineers build the world's longest sky gardens, 156 meters above the ground?
It must have been incredibly nerve-wracking. They had to be so careful.
What do you get when one of the world's most radical architects builds a railway station in the path of two natural disasters?
Building in earthquake zones is enough to make anybody, any engineer, nervous. But building in the shadow of a volcano?
And how is the world's most slender tower strong enough to survive winds of over 50 miles per hour?
Tall structures are prone to move. They're particularly vulnerable to wind. So the thinner they are, the more serious the threat.
This is the age of the extraordinary.
Where else can you swim from one skyscraper to the other 300 feet in the air?
Where ingenious engineers have unleashed unchecked creativity.
Everything in this building pushes at the boundaries of what's possible.
Building structures so outrageous, they defy logic.
The forces on this thing look like it should be torn apart.
Now, their secrets revealed. Discovering the incredible stories of their construction.
These are extraordinary feats of engineering.
To try and understand, how did they build that? In a tiny pocket of downtown Singapore, the challenge was set. To create a development of almost 2,000 apartments, where before it had been home to just 342. But on a site so small, engineers had to think outside the box. It could have been another boring tower block of identical floors and flats, but designers and engineers excelled, creating the tallest public housing residential building in the world, the Pinnacle at Duxton.
This building is a spectacular achievement on a site that most developers would have just walked past and not even given a second look.
A stunning 7-tower, 50-story apartment complex with 20,000 square meters of outside space. But not on the ground. Engineers did it by building the world's longest sky gardens, 156 meters in the air.
It's an amazing feat of engineering, but obviously there are going to be some risks that come with it.
A plot too small to build on conventionally. Thousands of prefabricated concrete panels, light enough to be lifted, but strong enough to support the 50-story towers. And sky bridges that were too heavy to be craned the 156 meters into the air. Just some of the complex problems faced during construction. So how did they build it? Like lots of cities, until recently, downtown Singapore was home to the financial district, but practically no one else. Keen to reinvigorate the area and attack the lack of affordable housing, the government launched a design competition to redevelop a tight and difficult plot. Architect Peng Beng's design was picked from over 200 entries.
The two main aims of the Pinnacle at Duxton was to really inject new life into this neighborhood and also to increase the population density of this area.
The plot was slightly larger than 2 football pitches and had been the site of 2 10-story residential blocks housing 342 apartments. The government's plan called for at least triple that on the same space.
The other huge consideration when you're building mass housing like this, where people are so densely packed together, is how do you make it pleasant? How do you make it a place that people actually want to live in?
The answer lay in a design that would push engineers to their limits. In a bid to increase capacity, while also creating attractive, comfortable homes, Peng and his team drew up a scheme that would become the world's tallest public housing residential buildings. Packed into the awkward question mark-shaped plot would be 7 163-meter-high towers. Each would be joined to the next at the 26th and 50th stories by 6 enormous sky bridges. 20 meters wide, these bridges would provide 20,000 square meters of greenery and outdoor space for the residents to enjoy. And with each measuring 500 meters long, they'd create the longest sky gardens in the world, if engineers could work out how to build them.
So the key question here is how to get the maximum amount of usable space into what is quite a small and irregular plot. And what they've done here is that they've arranged the building so as to kind of weave through the plot, just to really get as much into the available space as possible.
As construction began in 2005, the site threw up the first of many problems. There wasn't enough space to build the towers using conventional methods, and there was only one small access road in and out.
The site was so tight, it was so small, plus it was in the CBD area, the Central Business District area, which meant that, we would cause havoc and traffic jams during construction.
Already crammed with materials, heavy machinery, and hundreds of laborers, there was little space left. Casting the 50-story concrete towers on site would be impossible. The solution was to prefabricate off-site.
Using prefabricated technology was very important because the site was so crowded.
90% of the structural elements would be prefabricated in a factory 18 miles away. Then each piece would be transported to site. Instead of seeing this as a problem, the engineers turned it into an opportunity.
Sometimes when we do prefabricated, it's just a facade panel, but in this case, we designed the structure, the beams, and the columns into these panels so that as they were being put up, the structure was also being built at the same time. And the rainwater downpipes were installed into the panels that would drain water from the balconies and from the roof.
So, prefabricating the building off-site would overcome the issue of the small plot and allow Peng to hide away some of the services within the hollow walls. But it also created its own unique set of problems. Normally with a tower block like this, the concrete would be poured on site. It's the cheapest and most efficient way of ensuring the structure with its central support columns of concrete and steel is strong enough to brace the building. How would they be able to prefabricate concrete sections that were strong enough to bear the forces of these enormous towers, but also light enough to be lifted into position by the tower cranes? Coming up with a solution fell to the engineering team.
The tower crane capacity is less than 10 tons. And for such high-rise building, a lot of components are more than 10 tons. So what we have done, in order to reduce the weight of the component, we have developed a hollow core system.
Instead of being solid, these panels are hollow, making them lighter. They're also pre-stressed or compressed as they're being made, which makes them much stronger than normal concrete.
These panels are connected together in an interlocking way, just like a Lego block. And then we would put in high-grade concrete to seal up all the joints. So the joints would be cast in place, and when this cure, it would then act as a continuous unit.
Although building using prefabricated concrete is around 10% more expensive than pouring on site, in this case, it turned out to be a saving. Because although there were additional costs initially, the team got faster and faster at putting the towers together. Instead of taking 10 to 12 days, soon they were building whole floors in just 6.
It just illustrates that to make a building like this, you really have to approach it from a completely different way of thinking.
The next problem the team had to overcome was to ensure the 1,848 apartments didn't seem identical on the inside or out.
Part of our challenge was to use this way of construction, but produce something that looked totally unique and like as if it was impossible to be fabricated off-site.
The solution was surprisingly simple. They created 5 different styles of facade panels. then mixed them up. So as you look at the exterior of the 7 towers, the frontage appears random. In fact, it's anything but.
So you actually have an interesting facade, and at the same time you give the buyers and the residents a choice of units. So you can pick a unit with a balcony and you can buy that unit instead of having everything all uniform.
That idea of uniqueness doesn't stop at the front door. Prefabricating the towers gave the designers another great opportunity, which would allow the occupants to make each flat their own, but also to future-proof them for when the residents' lives change.
If we could create opportunities where people could make something unique out of their own units, and they could feel like, you know, they were part of the whole growth process, and the building didn't start to restrict you, but it started to give you a sense of freedom, a sense of choice.
So how do you build cost-effective tower blocks of affordable housing whilst also creating apartments that can be radically changed without radical building work?
In a typical high-rise, the columns and structure would take up quite a lot of space within the units. So we thought that if we pushed all of this structure onto the periphery of the units, the walls could then be easily taken down, so that if you wanted to, you could tear down all the internal walls and you can have just one huge apartment.
So by building all the structural strength into the flat's exterior walls, everything inside can be moved or even removed to open up endless possibilities depending on the needs of whoever's living there. And while each floor comprises of the same basic structural layout, the opportunity inside each flat on each and every floor is limitless.
Each of the floors is a variation of the same plan, and with that variation, you have individuality.
The next major challenge came in 2009, when the 7 tower blocks were ready to be joined together to create one interlinked scheme. On the 26th and the 50th floors, a series of sky bridges would connect one tower to the next, creating over 20,000 square meters of outdoor space for the residents, high up in the sky.
We created additional communal spaces in the air, which is actually at the sky bridge level. So we actually multiplied the amount of communal spaces available.
The residents now enjoy the world's longest sky gardens, but to put these huge links between the towers would be the biggest challenge yet for the engineers to overcome. Made up of giant steel trusses topped with concrete, the heaviest bridge weighs 350 tons, the equivalent of a Boeing 747. So how did they manage to get the sky bridges over 150 meters in the air?
It's no joke trying to get 200 tons of steel to the very top. They couldn't use a crane.
10 years ago, tower cranes couldn't lift such heavy loads, and the site was too cramped to bring in bigger ones. So the engineers came up with an ingenious solution.
To bring the bridges up to the correct location, we have to adopt a hydraulic crane system.
At the top of the 2 buildings where the sky bridge was being lifted between, there was a hydraulic jack connected to a winch.
Each sky bridge was attached to steel cables and then lifted into place using 4 hydraulic jacks and winches, 2 on each building. Computer-controlled, they all moved at exactly the same time and speed to lift the sections into place.
It must have been incredibly nerve-wracking. They had to be so careful.
If there was any wind at all, they'd have to stop and tie off both ends of the bridge. It took 10 hours to lift each bridge into place, completing an extraordinary piece of engineering, and in the process, changing the way the residents would live.
At the sky bridges, we have communal gardens, we have jogging tracks for the residents, we have play areas, and we also have elderly fitness stations, and we also have breakout corners, little gardens where people can sit down and chat with their neighbors.
Construction was finally completed in 2009 at a cost of over $205 million. The end result is amazing, a complex that serves the residents' every need. Neil Kim Powell was one of the very first people to move into the Pinnacle and has been here for 10 years.
Yeah, this place is unique, but it's pretty clean. It's very convenient. Everything is just a few steps away.
Over 5,000 residents from every walk of life live here. Now this vibrant community enjoys these sky-facing spaces high above the hustle and bustle of the city. A tourist destination, thanks to its stunning views. The Pinnacle at Duxton has successfully injected life into this district, and 10 years on, continues to be a model of world-class public housing.
The Pinnacle at Duxton is amazing. It's like an engineering magic trick. It's wizardry.
On Britain's south coast, the city of Brighton, like many English seaside spots with its piers and seafront, has been trading on its Victorian past. But in 2006, Brighton decided it needed a new, state-of-the-art landmark attraction to bring the city into a new century and millennium.
It's something that's going to have to really be built to stand the test of time.
It took 13 years of planning and would challenge both architects and engineers.
It's right on the edge of the possible.
But the results would be an extraordinary and innovative vertical pier that would allow visitors to walk on air.
It looks a lot like an amusement park ride, like it's supposed to be spinning or something, moving up and down really fast.
As well as being a marvel of modern engineering, the I-360 is also the world's most slender tower. A £46 million landmark that whisks 200 passengers up to a height of 138 meters in the face of buffeting coastal winds. Constructing at this kind of height, where even cranes couldn't reach, engineers had to think outside the box. So how did they build it? The jewel in Brighton's seaside crown was once the West Pier. It had been the finest Victorian pier in Britain. But throughout the 20th century, it had fallen into disrepair. And then in 2003, it was all but destroyed by an arson attack. Brighton Council were on the hunt for a must-see attraction that reflected the original pioneering spirit of the West Pier, but with a 21st century twist. Meanwhile, 60 miles away, the architectural wizards behind the iconic London Eye, Julia Barfield and David Marks, had come up with a new and exciting visitor attraction that they thought would be the solution.
The success of the London Eye was such that we got approached by many people wanting to replicate it. And so we kind of looked at what was the essence of the London Eye. And we then looked at how we could replicate that experience in a different form.
David and Julia's design for the I-360 would see visitors rise up into the sky to get a panoramic peek at the breathtaking surroundings. It was decided the perfect spot for it would be in the shadow of the remains of the old West Pier.
It is the site of the original West Pier, which is one of the only Grade 1 listed piers in the country. It was one of the most innovative piers in its time, and sadly it burnt down. So it was like the phoenix from the flames, really.
The final design for the I-360 would be a world first, as well as the tallest structure in the whole of Sussex. The 162-metre tower is made up of 17 stacked steel cans that get taller and thinner as you go up, held together by 1,336 bolts, weighing a combined 30 tons. The 900-ton tower supports an 18-metre wide toughened glass and steel pod that's 10 times the size of a London Eye capsule and can hold up to 200 people. It uses state-of-the-art cable car technology to drive the pod up and down at less than 1 mile per hour. Construction started in June 2014 on the beach, meters away from the sea. A tower of such height and weight would put enormous pressure on the base, so its foundations had to be super strong. But the engineers would first need to construct a stable area to build them on. Dr. John Roberts, who'd been chief engineer on the London Eye, was tasked with the job.
So what looks like shingle here, looks like the beach, in fact is just covering up the concrete. So that's actually the top of the foundation, the concrete is just there.
It would take just under a year to lay the foundations for the tower. The first stage was holding back the sea.
We're about 3 meters below ground level here, and the concrete foundation is 3 meters thick. So we had to dig an excavation more than 6 meters into the beach from the beach level. As you are aware, we're right on the edge of the sea. So when you dig below sea level, you usually come across water.
The team drove in concrete piles around a 24 square meter area of beach, and then started to excavate 7,000 tons of shingle. On hitting sea level, they had to pump out the water day and night until they reached the chalk bedrock over 6 meters down. Only then could they begin pouring the 4,000 tons of concrete.
We had to use concrete coming from every concrete plant in the whole of Sussex. I mean, this is one of the largest concrete pours that has been done in this area for many, many years. It was done in 2 halves, and even then, each half took more than 30 hours. You have to have a supply, and you have to have a backup in case the supply goes wrong, because once you start, you can't stop. So, in fact, nobody else in the whole of Sussex could have any concrete at all on those 2 days.
In 2015, with the foundations in place, the team made a start on building the main structure. Comprised of 17 gigantic steel cans, totaling 162 meters in length. Each of these steel cans or tubes differed in size and thickness and had to be carefully tailored according to where they appeared in the tower structure.
There's very few places in the world where they can be made. So the tubes were rolled and welded together in a special rolling machine in the south of the Netherlands.
It took over 18,000 man-hours of welding to make them, before being sailed by barge from Rotterdam across the North Sea, arriving right in front of the construction site.
You can also see here with this hole, this is a hole through the tower, and you can see how thick the steel is in the tower. This is 85 millimeters thick steel, and this is the bottom section. This is can number 1, the one that sits on the ground, of the 17 cans that make up the tower.
They may have got them there, but the next problem was how to put them on top of one another.
The big problem when you're building tall things is that the maximum lifting height of cranes is 100 meters, or about 330 feet. The I-360 is over 500 feet, or 160 meters.
So how do you build something that's taller than the maximum lifting height of a crane? The ingenious engineering solution was to build from the top down. A temporary 60-meter-high jacking tower was fitted over the spot where the I-360 would go. Then the steel can that would be the top of the tower was put at the bottom and lifted up by the 16-ton collar just high enough for the next can to go underneath. These two would then be bolted to one another before being lifted again.
So if you put number 17 in first and lift it up, and then put 16 underneath it and put the next one underneath that, you can build it that way instead, and you don't need a crane.
This procedure would be carried out again and again until the tower reached its maximum height of 162 meters.
The very last operation to put the last piece in at the bottom, the tower that you were picking up weighed 1,000 tons. So you had to lift 1,000 tons into the air to put the very last piece in at the bottom. it was done in just 10 weeks from start to finish.
Now they had to make sure it stayed there, despite being in such an exposed location and being battered by winds of over 50 miles per hour.
Tall structures are prone to move. They're particularly vulnerable to wind. So the thinner they are, the more serious the threat.
At 162 meters high and 3.9 meters wide, the I-360 is the world's most slender tower.
So you can imagine that when the wind blows, the structure vibrates. Think of it like a guitar string.
This phenomenon is known as vortex shedding, where turbulence caused by the wind hitting the tower causes it to vibrate. Unchecked, these vibrations could induce motion sickness in visitors and even cause metal fatigue in the structure itself. So John and his team devised a solution. They would add a 5mm thick aluminium cladding with a special finish to disrupt the flow of the wind.
The cladding has been perforated and deformed in a way that stops the wind blowing smoothly around the tube of the tower. And it's done to prevent vortex shedding.
It was time for the team to turn their attention to its crowning glory, the 18-meter-wide curved glass pod that would take 200 people up into the sky.
The point of this clever engineering is an observation tower that stands completely safely in a blustery and highly populated spot overlooking the English Channel.
The pod would need to be strong enough to carry passengers and survive all weather conditions whilst offering 360-degree panoramic views of the Sussex coast. The glass would not only be key to the view, but also play a major part in the pod's structure and stability.
So instead of glass just being added on as a window afterwards, the glass is a glass and steel structure, and it doesn't have any bracing.
Yeah.
The glass is bracing the structure. It's an extremely strong shape because it's curved in all directions. It's curved around the side, it's curved in all directions, and curvature gives strength, so it's a very strong shape.
Manufactured by hand in Italy, the toughened glass sections were sent to France, where they were assembled to ensure its complex geometry fitted together perfectly before being shipped to Brighton. In January 2016, the last pieces were put in place. Now it could be hooked up to its power source underneath the tower.
This is the machine room of the I-360. This is the heart of the project in terms of making the pod move.
The 94-ton pod is connected to an 80-ton counterweight inside the tower by 8 steel cables. Raised to the top by an electric winch, on the way down, it's much more sustainable.
The motor then operates as a brake to let it down gently, and the braking force regenerates electricity in the same device. So the motor becomes regenerative and generates electricity when it operates in reverse, and you get back a little over half of the electricity that you used on the way up.
After over 2 years of hard graft in all weathers, the I-360 was opened to the public in August 2016 and has taken over 1 million visitors into the clouds. It set the standard for must-see city attractions.
The whole process was a huge adventure and something that has been really, really positive for Brighton. It certainly regenerated the whole of the seafront.
Fabricated in the Netherlands using German steel, Italian glass, trialled in France and built on the British coast, the I-360 is an international celebration of innovative architecture and engineering combined. In Italy, in 2003, an ambitious high-speed rail project was proposed to improve train travel between the north and south of the country. At its heart would be a stunning new rail hub in Naples. A half-kilometre-long curve snaking over 8 new train tracks, a stunning, passively cooled corridor for millions of passengers to sweep through to its platforms below.
It's so perfect in all of its angles. It also communicates movement and action.
To create this ingenious building, engineers would have to work in the shadow of Vesuvius, the volcano that destroyed Pompeii and is still active. In an earthquake zone, to create a fearless architect's impossible design, and figure out how to keep the huge glass-roofed complex cool in the scorching Mediterranean summer sun. This is the Napoli-Afragola railway station. So how did they build it? In the late 1990s, with train travel in Italy on the increase, it was decided 4 new high-speed lines, 3 regional lines, and a single local commuter line needed to be merged together at a new railway station 12 kilometers from Naples. It needed to be capable of handling an increase from 10 to 30,000 passengers a day. But this would be no ordinary concrete box. This station would raise the bar for stunning looks, passenger experience, energy footprint, and seismic resistance. An ambitious brief called for a trailblazing architect, Queen of the Curve, Zaha Hadid, who had most recently designed the jaw-dropping Antwerp Port Authority extension.
When Zaha Hadid designs a station, you know it's not going to be an ordinary station.
The first challenge was that pulling all the lines together like this would normally completely cut off the area to the north from the area at the south. Filippo Innocenti was the project architect.
Quite an ambitious brief. The area is divided in two by the presence of the rail. So as it often happens, the rail, it creates a barrier in between two sides. So it is fundamental to provide a clear connection in between the two sides of this area separated by the railway.
Zaha's solution was to create a huge 30,000 square meter elevated passenger concourse on 5 levels that would bridge over all the tracks and effortlessly link the north and south. 500 meters long and 44 meters wide, the steel and concrete structure would rise up 30 meters to straddle the railway lines. Built from curved poured structural concrete, the design was so complicated it would take 3D computerization to make it possible. The 5 floors would be covered by a 500 square meter glass roof, cleverly engineered to let the light in and the heat out. These windows would flood sunlight into the atrium in the center of the elevated concourse, which would be surrounded by restaurants and shops. The entire place would be cooled without an air conditioning unit in sight by creating a system of underfloor pipes filled with ice-cold water from the natural aquifers 80 meters below. Not only would this be a place to catch or change trains, it would be a meeting place for the local community and 30,000 travelers every day.
Most large stations have an entrance hall with ticket machines and cafes and shops to one side and maybe an entrance hall next to the railway tracks on the other side. But here, they've put all of that on the actual bridge above all the railway tracks.
Construction on the €60 million project started in 2009, and the engineers working here had a constant reminder on the horizon of a clear and present danger.
In Afragola, we are quite close to one of the most important volcanoes we have in Italy, which is the Vesuvius, which is still active.
Mount Vesuvius is the only active volcano on mainland Europe. Its last eruption in 1944 killed 100 people, and the danger remains very real, with the potential to unleash the thermal power of 100,000 Hiroshima-sized atomic bombs. Volcanic activity isn't the only threat. The area is also at serious risk of catastrophic earthquakes.
The seismic area of Afragola is 3 in the range of 0 to 4, so still quite challenging.
Building the earthquake zones is enough to make anybody, any engineer, nervous. But building in the shadow of a volcano that destroyed Pompeii, yeah, you need to take that very seriously.
Builders made the 100,000 square meters of the station's exterior from 50,000 tons of poured concrete using formwork. This is where concrete is shaped using molds and reinforced by steel. Whilst it's strong and durable, it's also inflexible, making it more vulnerable to damage from earthquakes. If the engineers ignored this danger and created a continuous 500-meter concrete and steel structure, the station could fracture and collapse catastrophically in the event of an earthquake. But the engineers had a plan.
A more modern approach is to allow movement of the building. So in this case as well, where you have a number of flexible joints, what happens is it concentrates all of that movement at the flexible joints and then allows the movement energy to dissipate as heat. So it means that you get some movement there, you get some cracking as well, but you limit the structural damage to the rest of the building.
When you are exposed to seismic loads, these movements can be significant, can be in the order of 10 to 15, 20 centimeters, which means that the whole building has to be broken into elements, and this element has to possibly move one with respect to the other in the event of a serious seismic load.
They decided to divide the building into a sequence of separate zones, each no longer than 50 meters. And each zone could move independently by up to 15 centimeters. Tommaso Martellucci was the project's engineer.
These bridges, on the second, third, and fourth level, are connected at the hub with expansion joints that can absorb the stress and movement during seismic activity.
So the station was engineered to be tough enough to withstand an earthquake. But that wasn't the only force of nature engineers had to deal with. The design featured a continuous glazed roof to allow in as much natural light as possible. But here, in southern Italy, it would also be subject to the fiercely hot summer sun.
Building a glass structure makes a lot of sense when you have a lot of people that need to move through and it needs to be well lit, but that becomes a different situation when you're dealing with temperatures as high as 36 degrees Celsius or 100 degrees Fahrenheit.
So how would engineers overcome the challenge of filling the concourse with daylight, but cooling it in an eco-friendly way?
Naples can be extremely humid. There are days where the temperature goes really high and humidity is really unbearable. I have to say that I was quite nervous at the idea of having a building with a big glazed roof.
They needed a solution, because normal air conditioning would have come with huge costs, both to the budget and the environment.
What you're trying to do is to maximize the daylight that you can have inside the building and minimize the costs of the ventilation that you would have to fight against the solar heat.
Expert environmental engineers stepped in to solve the problem, using state-of-the-art technology based on ideas developed by the Romans 2,000 years before. First, they built internal shading fins into the roof, which filter the sunlight, holding heat above it and preventing it coming through into the passenger areas. A series of roof vents running the entire length of the station then allow the hot air to be funneled out.
The building is based on a mixed ventilation concept. It's combining natural ventilation together with mechanical ventilation.
On its own, this isn't enough to cool the concourse. The main cooling system is underneath the public area of the station in the service tunnel.
Here we are in one of the underground rooms at the heart of the plant that runs the station. One of the keys to the success of the building's energy sustainability is the air cooling and reverse cycle pump systems.
This passive air cooling system keeps temperatures down even on the hottest of days. Engineers drilled down 80 meters to access cold water from the natural aquifers running through the rock under the station. This is then pumped up and into a system of pipes similar to underfloor heating that have been laid throughout the station. But instead of giving off heat, the cold water absorbs it. It's then pumped back down into the aquifers, taking the heat with it.
A water source heat pump actually works very well in this situation. It's really good at absorbing the heat into the water and then running the heat out using the water as a medium. This was an idea that was actually developed pretty early on in the 1850s, but the first one actually wasn't built until about the 1940s.
In a world increasingly concerned about our environmental impact, these passive systems have come a long way, including creating the very coolest of chairs.
Within these seats, there is a system that allows hot or cold water to circulate and cool or heat the seats for the passengers.
Set throughout the station to allow passengers and locals to congregate, the elegant seating perhaps offers the perfect place to admire one of the most innovative uses of materials here. To cover the concrete surfaces inside and out, the designers wanted a smooth, weather-resistant finish that could flow over the building's ever-changing curves. They chose a material developed 50 years ago for domestic kitchens.
The outer skin of the building, as about 20,000 square meters, has been realized in Korean.
Korean is a brand of durable acrylic that most people might know from the kitchen worktops, but more recently it's being used to clad entire buildings.
And we were looking for a material that could be bent easily and to follow the simple curve of the building and to resolve the residual torsion of a number of areas of the facade. And the Korean was ideal for that because the continuous surface that allows to be bent at very low temperature, basically around 100 degrees, and can be put into shape very easily.
The panels were computer modeled and cut with 2mm tolerances.
Korean is made in panels and then they are bent in order to serve the purpose of allowing the curve of the facade. You basically treat it as wood panels. You can cut them and you can glue them perfectly without any trace of the junction between the panels. A very easy way of creating shapes with it.
In 2017, Napoli Afragola was finally able to welcome passengers onto its elegant concourse. For now, only 4 train lines are open, but by 2022, all 8 lines will be in service. This station will then be at the heart of the rail network in southern Italy, still keeping a low energy profile, but standing tall as a great example of how ambitious design and engineering can make life that little bit better. How do you build a glass dome big enough to house a mountain?
They really feel like a wonder of the world. There's nothing else like them.
What happens when a major station is completely taken apart and rebuilt during the rush hour?
This is like open heart surgery. The only problem is the patient is still jogging.
And how did engineers create the most outrageous building in all of Las Vegas?
You have to build something that gets attention. Your building is your billboard.
This is the age of the extraordinary.
Where else can you swim from one skyscraper to the other 300 feet in the air?
Where ingenious engineers have unleashed unchecked creativity.
Everything in this building pushes at the boundaries of what's possible.
Building structures so outrageous, they defy logic.
The forces on this thing look like it should be torn apart.
Now, their secrets revealed. Discovering the incredible stories of their construction.
These are extraordinary feats of engineering.
To try and understand, how did they build that? In the last 30 years, the Southeast Asian economic powerhouse of Singapore has seen its population double from 3 million to nearly 6 million. Finding the space to build here normally means building high.
The problem is, Singapore is a small island city, half the size of London, so space is at a premium.
When the government decided they wanted to give this booming population green space amongst the high-rises, engineers had to push the boundaries of what's possible. The end result was a solution packed with world firsts. Built on 1 million square meters of land reclaimed from the sea, 2 huge biomes, one the largest on Earth, engineered to keep visitors and residents cool in the searing tropical heat. Outside, a forest of giant super trees would be connected by a stunning skywalk, creating an avenue into the future.
Engineering doesn't get much more remarkable than Gardens by the Bay.
For the team that took it on, transforming a soggy patch of sand into an extraordinary state-of-the-art garden park would be the challenge of a lifetime. So, how did they build it? In 2007, work started on a huge new park for Singapore's residents. With over 80% of the population living in high-rise towers, it was desperately needed.
Cities need green spaces. Greenery absorbs carbon dioxide, it makes oxygen, and it just makes a city a more pleasurable place to live.
Working out where to build on this tiny tropical island was the first challenge that faced engineers.
You might well wonder how they found an extra 100 hectares in such a densely populated city. Well, they actually made it from scratch.
Today, Singapore is an island of 719 square kilometers. But a huge amount of the island's coast, the marinas, the airport, the industrial shipping ports, are actually built on land that has been created by the government. For the last 200 years, Singapore has grown by reclaiming land from the sea. But over the last 50 years, this process has accelerated, with Singapore now 24% bigger than the way nature intended. It was a 100-hectare parcel of this reclaimed land that meant the city could create a new green space. The plot, the size of 120 football pitches, was created in the 1980s by taking vast quantities of sand and rocks from building sites and seabeds and piling it up until it was above water level. This new land was then left to settle, but even by 2012, was still too soft to build big structures on.
The issue of reclaimed land is that you are effectively bringing in non-compacted gravel, non-compacted earth, and you can't really build onto that. And so what they did was actually put piles, long shafts beneath each of the foundations for the building structures they built, and they would extend down to the rock, to the base below the compacted earth.
These concrete and steel columns, firmly anchored to the bedrock, would be the key to supporting the two glasshouse structures. Now the architects and engineers could finalize the designs for building the park. It would be a project packed with innovation. Dominating the site would be the two huge biomes, or glasshouses. One with the largest unsupported glass roof in the world. Both would use a self-supporting latticework design with arcing beams to create the huge spans of glass covering 20,000 square meters of climate-controlled gardens. Outside, there would be a forest of man-made trees, reaching from 25 up to 50 meters in height. 18 super trees of concrete, steel, and plant life would be linked by an aerial skywalk towering over the groves below. The outdoor park would be planted with tropical species, which would thrive in the hot local climate. But the ambition for the two biomes was to house species from cooler, faraway lands. In Singapore, with its typical daily high of 32 degrees centigrade, that was a huge challenge. Glasshouses in cool climates work by using the glass to trap solar energy to heat up. This way, plants from much warmer climates can grow. Singapore's two biomes had to do something much more difficult. They had to somehow let in lots of light, but also stay very cool. Both needed to be around 25 degrees centigrade. But the huge flower dome with its plants from the dry Mediterranean spring climate of 4,000 kilometers north also needed to be very bright. With Singapore's humid, cloudy weather, the need for maximum light was the first problem the biome designers had to solve.
During the day, there's quite often a lot of cloud. The sunlight, it's not constant throughout the day, and it's not as much as the plants need to be able to grow. So we had to get every single ounce of sunlight we could into the conservatories themselves.
With daylight so crucial to the plants, the designers had to overcome the problem of how to support the huge roof spans without creating shade.
Most buildings need columns to stand up. It's how the load gets to the ground. But there is another way.
The solution to maximizing the light was to create a delicate curved framework to hold the 3,332 glass panels. Incredibly, this grid shell is self-supporting. It achieves this by mimicking an engineering design perfected by birds and reptiles.
A technique in engineering, an idea of using form and shape to provide the strength to the way a structure works. And you see it in nature all the time. An egg, for instance, is a perfect example of shape stiffness. The shell of the egg is that, a shell, and it's a three-dimensional surface, and it's very, very thin, but yet very, very strong. And that strength is created because of the form of it, the shape of it. And so we translate that idea into buildings.
By replicating the thin, strong, arcing structure of an eggshell, gravitational loads are evenly distributed down to the ground where it's fixed. The idea was a thin structure with no columns would allow in maximum light and self-support. But the huge size and that lack of supporting columns becomes a disadvantage when it came to actually building it.
Because we're creating this very large volume, there's a complexity in how the hell do you support it when you're gradually building it in stages, and obviously it all needs to be supported until it is the complete entity. A grid shell doesn't work until it's complete.
Engineers needed to work at heights of over 50 meters to assemble the roof structure. But a traditional scaffolding platform would have been complex and expensive. So instead, they came up with a simple but ingenious solution.
So they built a series of working platforms at substantial height. So the lower, flatter, the Mediterranean biomes are around about 35 meters to the top. So building something as a working deck which was 25 meters and then doing a regular scaffold on top allowed a massive saving.
As the structure was completed, the grid shell should have been strong enough to support the glass by itself. But there was a potential problem.
Structures by the sea need to be especially strong. I mean, think about it. With all of the rain that can come in and wind and storms, they need to withstand all of that.
Winds of over 100 kilometers per hour have been known to hit Singapore. So extra strength was needed to protect the fragile grid shell domes. The answer was to crane in 28 radiating steel arches, which would stretch over the roofs. These arches were then bolted together, connected at their bases to a concrete ring beam, which itself was anchored to the deep piles driven down through the reclaimed land. Then they were bolted to the latticework frame. The domes could now absorb any high wind pressures and avoid a catastrophic structural failure. Now, it was ready for the glass.
In the conservatories, we have the arched ribs, which provide the resistance to forces which are sideways, which shells are not particularly good at resisting. So there we've got two things combined, the shell stiffness, the shape, and the arched ribs, which are very stiff horizontally.
The success of the two grid shells is clear, with over 100,000 healthy plants thriving inside, as well as plenty of light. They need a maximum daytime air temperature of 25 degrees, going down to 17 at night. But with the Singaporean sun burning down at midday, these glass houses would naturally heat up to well over 40 degrees. How have engineers prevented this from happening?
Greenhouses like to get hot. I mean, that's the bottom line. You know, glass is a great holder of heat, and the solar gain is trapped, and it's a really great thing in a cool climate. But in a hot climate, when you're trying to make something cool, is obviously a big challenge.
The first line of defense was installing spectrally selective solar glass. This deflects 35% of the sun's heat, but on its own, it wouldn't be enough. So the next line of defense is bespoke blinds that roll out when the sun is shining. Again, engineered to minimize impact when not in use.
The shading is tucked within the ribs and furls right back, like a roller reef sail, folds right back into the ribs, so it can disappear. Again, for the very strong principle that on a semi-cloudy day, you need as much light as possible.
Despite greatly reducing the solar heat coming in, the biomes would still get hot enough to kill the plants in a matter of days. The solution was building in an underfloor network of cooling pipes.
This is something that we had learned from the Northern Hemisphere. So in the Northern Hemisphere, they actually do ground heating. We just reverse the entire process and cool the slabs.
To ensure the cooling system is as energy efficient as possible, biomass boilers burn organic waste from here and gardens and parks across Singapore. This helps generate the electricity to chill the water.
It's extraordinary that the whole Gardens by the Bay only uses as much energy as a Singaporean office building.
With the structure completed, the next engineering challenge was building a mountain the size of a 10-story tower block inside. And working out how to build this 35-meter structure out of concrete and make sure its sensitive plants could not only survive, but thrive.
So for the mountain in the cloud forest, it is actually made out of, it is a typical concrete wall structure. So first of all, we have the concrete, and then we have a material called hypertufa. Hypertufa is basically a mixture of cement and soil to give it kind of like an organic material that will help.
Clever engineering helped these biomes imitate the natural world of thousands of kilometers from here. But outside, the designers took inspiration from the jungles that once grew here in Singapore. They created an extraordinary alien forest.
Super trees. They're exactly as advertised, basically like trees on steroids, man-made, 16 stories high.
We were never trying to replicate a tree. We were trying to create a kind of modern 21st century version, an idealization of what a tree is in terms of using structures as steels and cables, but working in the way that nature does so, by being flexible and changing, and the way it supports nature.
These super trees aren't just steel and concrete, they've got plants growing on them, living on them. Somehow the designers have managed to incorporate a web of exotic plants into this man-made structure. All of these plants are incredibly heavy, so it's a fantastic piece of engineering there.
Rising between 25 and 50 meters into the sky, nothing like these super trees had ever been built before. With huge trunks and complex canopies, the engineers had to work out how to build them from scratch.
So what we tried to do was find a construction method which was repeatable. We build the cores, casting each of the pieces up one on top of the other, effectively using the same shuttering as you do in standard construction techniques. And once we built the concrete core, we then built the canopy on the ground.
To design the steel tree canopies, Neil drew on his experience building lightweight but strong staging for the world's biggest music acts, such as U2 and Beyoncé.
What's interesting about the world of rock and roll and staging is they are willing to develop ideas, look at ideas, which the other part of the building industry would not.
That fresh rock and roll approach helped the team create a canopy that was light, flexible, and easy to install.
We built a scaffolding system, built the surface up around it, and then we lift the whole of the surface of the super tree canopy skin up to the top of the concrete core in one piece.
These incredible trees aren't just for looks. Some contain photovoltaic cells to generate power. Others act as chimneys for the biomass boiler exhaust fumes. And they all help solve another problem caused by Singapore's land shortage.
One of the main functions of the super trees is actually to allow us to showcase vertical greenery. So as a lot of people know, Singapore is land scarce. So the only way for us to continue greening the country is actually to go vertically.
The trees hold 150,000 plants, and the whole incredible forest is completed by the 128-meter skywalk, threading its way through the canopy, high above the ground.
The whole thing is built on land that was once the sea. It's got one-of-a-kind structures on it, and it's all powered by offcuts of trees. Pretty impressive, really.
It took 5 years for engineers to transform what was once under the sea into perhaps the world's most stunning man-made wonderland. The ultimate in human nature. It's always tough building in the center of a busy city. But imagine modernizing a crumbling old mainline railway station in the middle of London, while 1 million people a week carry on using it. That's exactly the engineering challenge that faced the team tasked with reinventing one of the oldest railway stations in the world, London Bridge, which by the start of the 21st century was also one of the worst. Soon to be right below Europe's tallest building and hopelessly unable to cope with the demands of a modern city, something big had to be done.
This wasn't just a gentle reworking of the station. This was a complete rebuild.
The solution? was a bold scheme to sweep away history and demolish hundreds of Victorian arches, creating a stunning modern concourse that connects everything like never before. Up above, tracks would be moved and raised with 15 new platforms built, all on polystyrene.
This is like open heart surgery. The only problem is the patient is still jogging.
50 million people a year, over 800 trains a day, and one ambitious transformational plan. So, how did they build it? Ever since London Bridge Station opened with its 2 platforms in 1836, it struggled to keep up with demand. As London grew, so did the station, but there was never a coherent plan.
London Bridge Station is 180 years old in places. It was built in 10 stages over that long period, which means that every little piece of that, every little stage is slightly different.
By 2008, London Bridge was very much the poor relation to London's other major stations.
It used to be impossible to find your way around. So easy to get lost in, a real mess.
Very muddled, very old, kind of hodgepodge of different styles. It really wasn't something like St Pancras. It wasn't built with one grand vision, so it was a very kind of down-at-heel station.
With plans for Britain's tallest building given the go-ahead, London Bridge Station was about to find itself next to the Shard. With another 400,000 square meters of office space, adding to the explosion of skyscrapers going up nearby in London's financial district, the station had to be able to cope with more trains and a lot more people. The problem was the site couldn't get any bigger.
Well, the ambition, first and foremost, was to get more capacity, more trains through the station, through the existing viaduct width, because, of course, London's been built up since the station was made. So we had no more width, we had to get more trains through.
All of London Bridge Station is elevated above road level. Its 15 sets of tracks and platforms fan out on top of a massive brick viaduct, 15 meters high and nearly 200 meters wide. Back in 2009, hidden beneath this viaduct was a massive warren of Victorian arches, which supported the tracks above. Most were little used and would make way for a huge new concourse. This was construction phase 1 and would provide the much-needed easy access to all the station's platforms above.
If you think of the concourse, we had a full section of Victorian arches, and essentially what we did was just cut a slice out of the middle of that, and we did that bit by bit.
Extraordinarily, the demolition all happened right under the working station. The network of arches underneath the 9 platforms and 15 railway lines were all interlinked and relied on each other for support. A 75-meter wide swathe of these needed to be demolished to make way for the new concourse. But first, to stop the arches on either side of the demolition area from collapsing, 2 huge concrete retaining walls would be built. With this in place, they would be able to bulldoze a 185-meter-long corridor through the arches and create a new space twice the size of a football pitch. This would become the all-new street-level concourse. Then huge new concrete columns would be built to support new platforms and tracks that would sit on top. These columns would need to support tens of thousands of tons of platforms, trains, and people, so they needed to be very strong and built to last. The construction team was managed by Adrian Tooth.
To support the amount of weight that comes down those columns, we have to drill what's called piles into the ground.
Inserting piles into the strong bedrock below for added strength wouldn't normally be a problem. But here, running right under the site, is the London Underground.
Some of our piles that we had, our 50, 60-meter piles right down into the ground to build our concrete columns, were really, really close to the Jubilee line. So what we had to do is, while we were piling, we had monitors on the tracks at the Jubilee line. So if the track started moving, we really knew we were in trouble.
With the concourse build well underway, the engineers now needed to figure out how to relay the train tracks that ran over it, while 200,000 people a day continued to use the station. On top of that, with the predicted rise in passenger numbers driven by London's booming economy, the rail networks wanted more trains to run through across London, and fewer trains to terminate here. The existing track layout needed a complete rethink.
When we inherited the station, there were 15 platforms. So there were 9 terminating and 6 through. But to realise Thameslink, we had to change that to 6 terminating and 9 through. And that meant that every track in the station had to change position.
In order to achieve this switch around, the tracks all needed to be at the same height. But they weren't. The terminating lines were 2.5 meters lower than the lines with trains that continued on through, so they needed to be raised. But a big chunk of the track would still be held up by the 180-year-old Victorian brick arches, and these wouldn't take the weight of the concrete needed to raise the tracks.
So when we assessed the capacity of the existing arches, they could only take a relatively low load. So if we then needed to increase it by, say, 2.5 meters, if we had done that in something like concrete, you're adding a massive amount of weight to the top of those arches. So they weren't capable of taking that. So we had to find a new way of doing it.
They would also need to carry the weight of the new platforms.
They needed some kind of structural filler, something lightweight that could take the compressive load.
The substance they turned to was surprisingly simple and very common.
They used this, not a coffee cup, but the material it's made out of, polystyrene. The surprising thing about polystyrene is, although it's incredibly light, it's also incredibly effective when it's pushed down.
We built a foundation and then we put polystyrene wrapped in a plastic wrapping that has a 120-year design life. And then we built concrete around it. It gave us the structure for us to get the tracks up to the level they needed to be, but it also was light enough so that it could sit on the arches below. So these are the kind of innovative solutions that we had to come up with, working on a station like this, where you have very, very old infrastructure next to very, very new.
The polystyrene itself is actually carrying a concrete slab, it's then carrying the platforms, and it's also carrying the weight of the trains.
Achieving all this and keeping the station open and safe meant taking one step at a time.
The complexity in undertaking demolition, building new platforms, canopies, while you've got trains running in and out is huge. What we did at the beginning was we took 2 platforms out of use. We would put the hoarding up, set up our work site. We would demolish those platforms and tracks and the arches beneath them, and then build up.
The new design and layout called for 6,000 meters of roof to snake over the new platforms. But the constraints of the site gave rise to yet another problem.
How do you build a new platform and a platform roof on site when you have no space to do it?
The answer is, you don't.
Various elements of the station build were prefabricated off-site. For example, some of the platform units and also the canopies were fabricated elsewhere and then brought into site. So the advantage that gave us was that it meant less on-site construction where we had limited space.
The platform canopies came in 3-meter-long modules and were put together like a DIY flat pack.
They came with all of the containment that carries the wiring within them. It came with cameras, speakers already set within them, all the lights were set within them. So it was just a process of putting one next to the other, filling in the gap between, and then wiring it all together. So very quick.
In just weeks, each pair of tracks was raised, the platforms built, and the canopy completed. It required the different teams on site to work like clockwork.
You don't just have a designer making the design and handing it over to the contractor to build it however they want. They're thinking about the building process as part of the design. This is architecture meets engineering meets project management.
The teams also worked to ensure the historic Victorian features of London Bridge Station was celebrated alongside all the modern engineering. Like the 150-year-old columns, each supporting 4 connecting arches and the platforms above, many of these survived to become part of the new London Bridge experience. Where they couldn't be kept, they were mirrored in modern materials, but clearly defining the new from the old.
From an architectural vision perspective, it was important to repeat the historical importance of the original arches. So if you walk through that area, you'll see the original brickwork arches and then the new interpretation in board-marked concrete.
Thanks to the skill of architects, engineers, builders, and the rail company, the London Bridge Station modernisation finished on time in 2017.
This project was an amazing endeavour across all of the different disciplines. There was about 1,600 people worked on the project. In terms of numbers, I think there's 24 kilometres of platform edge that we put in.
We now have 10 times as much space as we did originally, so the journey that this station has come on is huge, and it's one that it's been great to be part of.
From being unable to keep up with even yesterday's demands, London Bridge has been readied for tomorrow, while retaining the best of its Victorian character. It took 8 years to reinvent this station as a shining beacon of railway efficiency. The ambition and achievement recognised with the prestigious award, Building of the Year 2019. In the beating heart of London, modern engineering and ingenious design has succeeded in creating a stunning station, fit to serve the city's travellers for another 100 years. Las Vegas, Nevada, where a gambler can take a quick tour of some of the world's most iconic structures before deciding where to splash the cash.
Every building is more extreme than the last, and it makes sense because this is Las Vegas. I mean, you have to build something that gets attention, and your building is your billboard.
Copies of famous landmarks might get you noticed on Vegas's main strip, but how do you make a big impression if your building plot is on the outskirts of town?
To get noticed in Vegas, they had to build something impossible.
But this was no casino. Here, a man was inspired to build a hospital so extraordinary it could also be a fundraising event space.
I said to my wife, Camille, if we're going to do this, we got to make a statement.
The result was a building almost as complex as the organ that inspired it.
There are 2 halves of this building. Just like the human brain, the left side is ordered and logical, and the right side is wild and creative.
This is the Lou Rouveau Center for Brain Health. Designed in California, engineered in Europe, fabricated in Asia, and built on 2 acres of Nevada desert. It's the show-stopping outcome of 65,000 hours of engineering effort, $80 million, and nearly 900 tons of steel. It doesn't look possible. So how did they build it? The building is the brainchild of American entrepreneur Larry Rouveau, driven to create it after experiencing the moment his father, Lou, was diagnosed with Alzheimer's disease.
I just said I would never want anybody to go through this humiliating, lack of dignity experience that I just went through. If I could ever do anything, I would change that.
Larry decided to build a new hospital for degenerative brain disorders. As well as being ideal for treatment and research, He also wanted it to be visually so extraordinary that people would want to hire it for events. To design it, Larry turned to one of the world's greatest architects, Frank Gehry. Aged 81 at the time, Gehry was very much at the top of his game, as one of his projects, the Guggenheim Museum in Bilbao, had recently proved.
The initial day he was here on this site, I told him what I wanted. He took out a yellow piece of paper and he drew it, and that's what I got.
A sketch was one thing, but Gehry already knew this building would be his most complex to date. So complicated, in fact, that only the world's most expert engineers would be able to pull it off.
Frank said to me, "So what would you say that if I told you this building, a building like this has never been attempted before? It will be engineered in Israel and India and Germany. And then it's going to be sent through the internet, the design, to China. And then we're going to ship it over here in 555 pieces, no two alike."
Budgeted to cost $80 million to build, the structure appears bent and twisted, as though it's collapsing in on itself. At one end, the extraordinary facade gives way to reveal a much more conventional building underneath.
Looking at the building overall, if you sort of divide it into two parts, the part with the sort of metal cladding, very chaotic and disorganized looking, that's our event center. The side where the medical care actually takes place is actually quite orderly.
The clinic building is actually a conventional 4-story white block structure, partially hidden behind the curving steel facade. But the south wing had an altogether different purpose, and so needed a different approach.
When we started out on the design of the building, I told Frank, most hospitals, most clinics, when they close at night, what happens? The janitors come in. Instead of janitors, I want ambassadors to come in. People will rent this building for weddings and events, and we live in Las Vegas. We could rent that out, use this as a revenue source to fund our research. So somebody can come here, rent this space, and feel good that they're helping a charity, and it's beautiful.
Gehry's vision for a must-see event space was a structure that was as jaw-dropping on the inside as it was on the out. The challenge for the engineers was to figure out how to build it with as few columns and straight walls as possible.
As you see, it is a huge structure without any support in the center. And the way it's manufactured in pieces, each piece, it varies from 2,000 pounds to 10,000 pounds, each piece. And they are made of steel, fabricated of huge pieces, from the size of a couch to the size of a car, almost.
The huge sections were heavy because the steel needed to be strong enough to compensate for the lack of internal supporting columns.
The amazing thing is that the curved panels on the building actually provide a lot of the structural support.
To achieve this, the panels needed to be very tightly bolted together. So engineers perfected a new way of connecting the frames.
It was designed on friction. The plates has to be tight against each other without air gaps. And that's the reason why we have to have so many bolts in each pieces.
But the construction team's problems were far from over. The people required to create these unique components were so rare, they were dotted around the globe. Dimensions were being calculated in Israel and India, then the parts being made in China. The builders on site needed to be sure they were bolting it together in the right way.
Just try and think about the level of precision that a project like this would need. If anything was wrong, they'd have to dismantle the whole facade and put it back together again. So the sequencing, the fabrication, and the construction were really key to making this work.
The answer was to barcode each piece of steel. Once the steel was on site and was offered for assembly, the individual barcodes would be scanned and transmitted to the main engineering team in Germany, who would cross-check to make sure the right pieces were being joined.
This system meant that every piece could be checked before it was slotted into place.
1/16 of an inch in one corner, off the other side, it would be a disaster. It had to be perfect.
Having worked out how to build the complicated steel frame, the engineers then turned their attention to the facade. Once again, architect Frank Gehry had a vision.
Frank said to me, since you're in the desert, I want the immediate impact. I'm going to use stainless steel.
But 1,800 curved stainless steel tiles on a building in a desert where the sun burns hot for 3,800 hours every year wasn't without its issues.
Stainless steel is super reflective. There's a risk that you'll get blinding light firing out in all directions, which is not what you want when you're building sitting on a major road junction.
The solution was a special angel hair finish applied to the steel. Micro scratches brushed into the metal with a stainless steel wire brush that helps diffuse the light.
That's what makes it absorb the sun instead of reflecting it as much. So it doesn't really shine in people's eyes.
With passers-by protected, the team turned their attention to making sure the light on the inside was also just right. Dr. Wint is in charge of patient care at the hospital.
The natural lighting, I think, is really important. It gives less of an industrial feel, and often that's important for some of our patients who don't realize they're ill.
Engineers installed 199 windows, allowing a lot of natural light into the hospital and event space. But you can have too much of a good thing.
Las Vegas is in the middle of the desert, so you're talking about some pretty high temperatures that can go as high as 40 degrees Celsius or 104 degrees Fahrenheit.
To protect occupants from too much heat and light, every window has blinds installed, each tailored and controlled by a central management system that's linked to monitors in the thermally reflective glass. It's this adaptability to harsh conditions outside and its sensitivity to those inside that helps make this building so outstanding. The best place for those most in need of a superbly engineered health center.
It is very unique and different and beautiful building, and somehow in a different way, very peaceful.
The Lou Rouveau Center took 3 years to complete and was the most complicated of Frank Gehry's designs yet for his engineers to build.
This building was exactly what I wanted it to be. It gave us the credibility. People knew we were serious. You want to build a Frank Gehry building for a disease, they know you're serious.
We built a building that you just cannot miss. You have to talk about this building when you pass by it, and hopefully people will also talk about what's going on inside. So I think for sure that part of the idea behind this building and its very unusual looks was to say, we are here, this disease is here, we're fighting it.
I love the fact that something that is this housing work that's so important is also housed in a building that looks amazing as well.
What happens when an ambitious builder tries to join two skyscrapers high up in the Manhattan skyline?
You can't call a friend and say, hey, what did you do the last time you built a bridge 300 feet in the air in New York City?
How does this huge wing-like roof not take flight in gale-force winds?
The whole canopy has an ability to move 15 to 20 centimeters.
And how can a building be constructed without a corner in sight?
It kind of goes against everything we think engineering should be.
This is the age of the extraordinary.
This house always is on the verge of falling down.
Where ingenious engineers have unleashed unchecked creativity.
Everything in this building pushes at the boundaries of what's possible.
Building structures so outrageous, they defy logic.
The forces on this thing look like it should be torn apart.
Now their secrets are revealed, discovering the incredible stories of their construction.
These are extraordinary feats of engineering.
To try and understand, how did they build that? New York. With the total area of buildable land worth over $1.7 trillion, its eye-watering prices have created one of the world's most memorable and expensive skylines. With space at a premium, it's forcing developers to come up with groundbreaking solutions to make the most out of even the least inviting scraps of land. Developing one awkwardly shaped plot in Midtown Manhattan tested engineers to their limits, leading to panic on the streets.
Here, the fire department, they pull up and the guys come screaming and they're running in and we got a call. One of the buildings is falling down.
And creating the city's first sky bridge in 80 years, giving rise to one of New York's most incredible new skyscrapers. This is the American Copper Building.
Building two skyscrapers, wanting to join them in the middle, and then deciding that actually you want them bent, that is next level.
In 2013, developer JDS had its eye on a plot next to the river that should have been prime real estate. But the site came with a major problem: New York City's zoning laws. The rules that decide what can be built and where.
The zoning of this site was prescribed before we bought the site. That approval prescribed the exact footprints of the tower and the exact heights of the tower. They assumed by prescribing the footprint and the height that they were prescribing the exact building shape. But when we bought the site, we didn't want to create two buildings. We wanted to create one building.
There was an existing building in the corner of the plot, and a piece of land that had been zoned as a park. So how could they create their dream of a single building?
We didn't want anyone to be going to the gym in their neighbor's building. We didn't want someone going to a lounge or going to visit someone else in a neighbor's property. We wanted to use the scale of the property and the block to create one community.
JDS brought in Greg Pasquarelli from Shop Architects to find a solution.
When our client bought it, he said, I could go through a rezoning, which takes many years and has a lot of risks and it's very difficult. Or he said, can you come up with something with these handcuffs on? And that was our challenge.
They could have built two towers, but they came up with a much better idea.
There end up being a lot of great ideas, a lot of terrible ideas. And what usually ends up happening is one of the terrible ideas turns out to be a really wonderful one. And it's terrible at first because somebody says, let's build a giant bridge between two buildings, hundreds of feet off the ground. And for those of us that have to pay for it and figure it out, we go, no, let's not do that. But of course, as you start to wrap your head around kind of all the different aspects that could make it possible, you start to realize that it's actually very approachable. And the way we approached building the Sky Bridge was the same way we approached building everything else, which is kind of one step at a time.
It would be the city's first sky bridge in over 80 years. Joining two giant skyscrapers 90 meters in the air on the banks of the East River on a site prone to flooding was always going to be an engineering headache. But it was also an opportunity.
The idea was we could make a sort of amenities package or a shared space that would be sort of typical for each building, or if we built a bridge, we could build one phenomenal one that brought everybody together. And so getting that designed and built and making it work was the greatest challenge, but I also think is the greatest success of the project.
The easiest way to connect the two towers would be with a straight line. But that would mean going over the existing building, which they didn't own. The architects came up with a gravity-defying solution. They decided to bend the buildings.
How did they bend the towers? That's the real question.
They bend towards each other, right? One on the long axis and one on the short axis. It moves the edge of the West Tower out to the corner of the property line so that we can actually connect the two buildings with a straight line. Otherwise, our bridge would have had to be kind of L or V-shaped, which is obviously much harder still to do.
By bending the two towers, they'd not only overcome the zoning issues, but also the engineering ones.
Making small adjustments is a great way to make a big change. A couple of inches can quickly become meters, and it's something that clever designers can use to their advantage.
And that's exactly what they did here. By slightly moving each floor closer to the other building as they go up to the sky bridge, and then moving away again, they were able to bend the buildings.
We were able to solve both of those problems with these really elegant architectural moves.
In 2012, work began preparing the site for construction. It was clear from the start this was going to be a tough build. The site was right next to the East River, a location that had previously flooded.
It's in an area that's subject to hurricanes. So in 2012, there was a very large hurricane, Hurricane Sandy, which affected New York. And during that hurricane, this actual site was flooded before the building was constructed. So that's really highlighted two of the main risks to the construction, the wind and the water.
The man who had to face this challenge was Michael Jones.
The foundation of the building was kind of a monster process on our end to build it. We're very close to the East River and the water level is very high. So to dig a hole as deep as we had to dig it and do all our foundation elements was a serious challenge.
Michael and the team had to dig down 15 meters. But with the water table only 1.5 meters below the surface, they needed to stop the site from flooding. The engineering solution was to create a huge concrete structure to keep the water out.
What you do is you create a perimeter wall around your site from the ground level. You can push steel sheets and you push those down into the ground and they interlock. And so you more or less build a bathtub with no bottom. And then the water level is inside the bathtub is the same as it is outside. So then what you can do is you drill wells down there and you de-water inside of your bathtub. You can locally bring that water level down by putting a pump. You have to kind of artificially drop the water level. And to do that with a few cups of water is really easy. To do it with a few million gallons is difficult.
It took 1.5 years to do it. But with the bathtub built and the foundations in, they could turn their attention to the next big engineering challenge: building the bending towers.
Generally, a leaning building is very much a bad sign. And the designers would very much have had to have factored in the kind of sideways forces that are caused by something leaning. But there's two things to consider, and that's that they've designed a building that's able to lean, but also that that building is going to be leaning throughout its construction, which means you have to really think about the stability of the final building, but also all the intermediate stages during construction. So it's an engineering feat.
The person making sure this bent skyscraper didn't come crashing down was structural engineer Susan Hamos.
Because of the leaning of the building, every floor we had to tie back to the shear walls, which shear walls means they take shear, they take horizontal load, they take shear from the wind loads, shear from the seismic loads, and shear from gravity loads. You imagine if you put something like this wants to fall down. So we had to put some rebars to pull it back to the vertical long concrete walls that were designed to take all these horizontal loads from the gravity.
Although the building bends, the lift shaft and the shear walls stay vertical and act like a spine, taking the force of the floors as they create the bending skyscrapers.
The main structure, which is the core, the elevator core, and the shear walls, which are massive structures, those stay straight, but all of the columns were on an angle. So we got really good at building columns on an angle.
As the extraordinary skyscrapers took shape on the Manhattan skyline, they didn't go unnoticed.
This tower, the East Tower, goes about 8.5 inches per floor. So by the time we are really offset maximum distance, we're over 20 feet, 22 feet, I think it is, out of plumb before we start working our way back. And that's the sort of visual thing that people really weren't accustomed to seeing.
The bent shape of the skyscrapers caused panic as the buildings were going up, which is something that the main builder had to deal with.
One day, we're down there, we're all working, and you hear the fire department, they pull up, and the guys come screaming, and they're running in, and it's a little chaos for a second, and we're trying to figure out what's going on. And finally, I grab the guy, I go, "What's going on? What's happening? I'm in charge here, what's going on?" He said, "We got a call. One of the buildings is falling down." And I kind of stopped, and I had to think about it for a second. I go, no, it's supposed to be like that. Showed him pictures and renderings of the building and showed him the plans and everything, but it's such a unique architectural feature that people didn't know how to respond to it.
Once the builders had convinced New Yorkers the towers weren't collapsing, they still faced one of their biggest challenges: the Sky Bridge. Central to the design, the Sky Bridge, 90 meters in the air, would join the two towers together, making one community.
The bridge is several layers. There's private terraces on top, there's a public lounge in between, there's a pool and hot tubs, you can kind of swim from one building to another. And then below all that, the bottom level of a bridge, we use to transfer mechanical water, and we use emergency generator power. We transfer from one building to another. And that's really my favorite part, is that it allows us some kind of leeway in terms of where we put equipment, so each building doesn't act isolated to each other.
The bridge came with some serious engineering challenges. How would they stop the hurricanes that regularly hit New York, tearing it apart?
The biggest design constraint on tall buildings in New York is wind. So buildings move back and forth towards each other and away from each other. The total movement between the two buildings is about 12 inches. 12 inches is in a windstorm. So that movement is our number one challenge. From a structural perspective, that Sky Bridge is like putting a toothpick between two rocks.
Skyscrapers are built to cope with high winds, and at the top can move around a meter in any direction. Fine when they're not fixed to another building. But here, two independently moving towers would be linked by the bridge, and when they moved, they could rip the bridge apart.
Is it possible to put a bridge there? We said, of course it's possible. So how will we do it? And we said, no problem. We'll connect it to one building and we let it slide on the other. So when the wind is hitting the two buildings, one would move out, the other one would move in, and we don't want the bridge to buckle, to pop out of its place. So we have to slide it on one side.
Their solution was to join only one side of the bridge to the towers and balance the other side on huge Teflon plates, letting the bridge slide in and out of the East Tower.
It slides on these giant Teflon plates that account for 28 inches of movement in total, 14 in any given direction.
Now they knew it was possible. All they had to do was build it.
Unfortunately, when you're doing something unique like this, you can't call a friend and say, "Hey, what did you do the last time you built a bridge 300 feet in the air in New York City?"
Building a 90-meter high and 75-meter wide scaffold tower between the buildings to allow construction of the bridge would be difficult. So they decided to build a temporary bridge from which they'd construct the real one.
We were trying to figure out the best way to do it, and it started with someone was supposed to bring a football in. We were going to tie a string to it and kind of throw it from one building to another, but I think we forgot the football that day, so we took a stick and wrapped it up with a bunch of literally small string, made sure everything was clear below, everything was safe, we were good, threw it from one building to another, and so we had one string. Then we pulled back a string that was a little thicker. Then we pulled back a rope, then we pulled back a thicker rope, and then we could finally pull back the steel cable and literally just started weaving the cable back and forth until we got it. From there, we could work off there and start building the bottom of the bridge, build another platform, build the next level of the bridge, and so on.
With the temporary bridge in place, Michael then had to figure out how to lift the huge sections of steelwork 90 meters into the air.
We were limited with what equipment we could actually lift it with, because as you can imagine, lifting something very heavy, probably 40 to 60 tons at that height, over 300 feet in the air, requires a serious piece of equipment, and you can't always fit serious piece of equipment in New York City.
To lift the giant steel trusses, the skeleton of the building, into place, the builders attached a tower crane to the skyscraper to stabilize it against the wind.
Now that we know the maximum piece of equipment we can get in here, how do we break the bridge into pieces that that piece of equipment can lift, and so that we can then construct it?
210 tons of steel had to be hoisted the 90 meters up, one piece at a time, to where the construction crews could connect them. With the sky bridge in place, work began on fitting the extraordinary copper facade.
They're called the copper buildings because they're covered in over 4 million pounds of copper.
Like everything else on this project, creating that copper finish was not going to be easy.
First time this idea was presented, we thought we'd have to put copper plate on the outside of the building. And we did the math on how much copper we'd have to buy, and then looked at the raw material price of copper and realized that we'd have to pay more for the copper just to get it here than we paid for the property itself, which means that we couldn't afford it. And so what we ended up doing was coming up with a pretty unique laminating structure where the copper face, which is very, very thin copper foil, actually thinner than what's even on a penny, and it is laminated to a fireproof core, and then on the backside of that core is stainless steel.
The raw copper is then left untreated and open to the elements.
Copper's gone from shiny, penny-colored, and it will patina and continue to turn green.
The rest will be done by the weather over the next 50 years.
It's gonna be beautiful. I can't wait for that. I love the copper, but there's something very American about that color green, especially in New York. It reeks of kind of old, beautiful New York buildings, all the flashing, but ultimately it reminds me of the Statue of Liberty, so can't wait for it.
The designers and developers have truly built the incredible from the impossibly difficult.
The American Copper Building takes its place in the New York skyline as a testament to how ingenious engineering and clever design can create amazing living spaces in one of the world's most crowded cities.
Two spectacular buildings forming a single iconic project. It's a real engineering achievement.
Taking this kind of restrictive set of rules and celebrating it into something that looks beautiful and inspiring and makes people wonder about it. Whenever you can do that as an architect, I think that's something you should strive for.
"5,000 miles from New York, in the ancient Greek city of Athens, engineers and architects have been battling Mother Nature to create an enormous 10,000 square meter floating roof.
To my knowledge, it's the first application in the world.
Over €500 million created a cultural center for all Athenians. Complete with a new hill with a public park on top.
This isn't just about creating a building. You're creating geography.
And all of which has to be tough enough to withstand any potentially devastating earthquakes.
Building in an earthquake zone is a dangerous game.
So how did they build it? In 2006, the Stavros Niarchos Foundation, a wealthy philanthropic organization, wanted to give a new home to Greece's National Opera and National Library. They wanted somewhere that would inspire the people of Athens. Eli Andropoulou helped manage the €566 million grant given to build the Stavros Niarchos Foundation Cultural Center.
Pushing the boundaries of architecture and engineering wasn't a goal in itself, but it was a very important means to achieve the vision of the SNFCC. So we didn't want to just provide new premises to these two national organizations. We wanted to give them a new home, which would become a landmark. There were a lot of risks taken. The people involved in the project were very passionate about pushing these boundaries, and they certainly had the expertise to do so.
The foundation turned to the company that had transformed the London skyline with the Shard, the Renzo Piano Building Workshop. Giorgio Bianchi oversaw the project.
We had in mind this idea to raise the land in some way and hide the opera and the library under something like a hill. The hill was the park. I create my hill, and on top, I put the solar canopy. And then I plant my park. And here you have the opera house and the library. Easy.
Building it would prove to be anything but. The futuristic buildings would hide behind a massive 32-meter-high artificial hill. At one end, the new earthquake-proof complex would be home to the Greek National Library and the 28,000-square-meter National Opera building. It would be topped off with a huge square floating canopy, 100 meters long, that would protect the complex from the fierce Greek sun and generate electricity to run it from 5,700 solar panels. Many of the building techniques needed had never been used in Greece before.
There were certainly many challenges during construction because we were pushing these boundaries in engineering. The canopy was certainly a very challenging element. The hill in the park, the seismic isolation of such a large building, all of these challenges were overcome and led to great innovation.
One of the most important challenges was going to be protecting it from the Earth itself.
Greece lies on several fault lines and has a long history of earthquakes. Traditionally, though, Athens has remained unscathed. Unfortunately, that changed in 1999 when an earthquake hit and killed 143 people.
In 2018, Greece was hit by nearly 300 earthquakes. Quakes greater than 6.3 on the Richter scale can destroy a building.
If you're creating any new building in Athens, you've got to take earthquake risk seriously.
Structural engineer Gregory Pinellis was part of the team that took on the challenge.
Greece has actually 50% of the seismicity in Europe. So it's obviously a very seismically prone area. Such a complex structure was obviously a challenge, not only because of its complexity, but also because of its criticality, considering that it is an opera that has thousands of people inside when in operation. So seismic safety was a very big issue for the design of this building.
With millions of people expected to visit each year, they couldn't take any chances.
The purpose of any structure is to carry load or forces from where they are and down into the ground, and that's true of anything from buildings, bridges, chairs, and my skeleton. But when you have an earthquake, then what's happening is that the ground is shaking violently from side to side, and it's that sideways force that has to be carried down into the foundations. So if a structure is in an earthquake zone, then it has to have a way to resist that sideways motion, or it will fall down.
Most buildings are made to resist forces from the top down. But with an earthquake, you get sideways or lateral movement that can easily destroy most structures.
Both the opera and the library are actually seismically isolated. Seismic isolation is like you put the building on rollers. So when the earth moves, because the earth moves, not the building, it moves underneath and the building stays the same. A very easy analogy for the non-engineers is when you have a wooden table and on top of it a toy truck, and you move the table and the truck stays without movement. The table moves, or when you take the tablecloth under the plates, and the plates stay, if you can do that.
All well and good in principle, but how do you pull it off with two huge buildings?
Here we are in the basement of the opera. We are at -2 meters from the sea level, from the ground floor. Every column of the opera and the library has a seismic isolator underneath it. And underneath the seismic isolator, there is a concrete pedestal, and then we are standing on the foundation of the building. So the whole building is seismically isolated from the ground, so that when the ground moves due to earthquake, the building remains stable. So when the earthquake happens, the pedestal and the ground moves with a tolerance of 35 centimeters back and forth each way. One of them is actually the largest one ever installed in Europe. The critical thing is how we design all the mechanical and electrical and architectural features of the building that connect the ground to the upper stories so that they can follow this 35 centimeter movement.
Allowing a building of this size to have 70 centimeters of movement requires an awful lot of forward planning. Every wire, every pipe that's going in and out of this building requires an extra flexible section in order that they don't break when the building's moving.
Every wall joint and every staircase has to have a movement gap, which they then fill with silicon filler. When the building shakes, the silicon breaks. That's a lot of filling and repair work, but it's much better than the alternative.
Their next challenge was to create the enormous 32-meter-high hill that gives the building its signature shape.
This isn't just about creating a building. When you're making a whole new hill, you're creating geography. They've actually altered the skyline of Athens.
This 300,000 cubic meter hill is made up of enough dirt to fill 120 Olympic-sized swimming pools. 3,500 gravel pillars had to be constructed underneath to hold the soil in place and prevent landslides. Then, the top was planted with over 1,000 trees. The effect of creating the park was to lower the local temperature from the shade the trees generate. The hill, though, had another purpose too.
It was just to give back to this part of the city the idea that they have the sea very close, and they can use this area to get to a point that where the sea is visible again.
At the summit, looking over the Mediterranean Sea, sits the engineer's greatest achievement, the canopy. A huge technological marvel that needed engineering solutions used nowhere else in the world.
It is a structure that's 100 meters by 100 meters in plan. The magnitude of this and the need to create a very large structural span of more than 75 meters clear span led to a lot of innovations.
There are 750 panels creating a 100 meter by 100 meter canopy that simply floats on the Athens skyline. It's a beautiful piece of engineering.
As well as being beautiful, The huge 4,700-ton canopy had to survive the Mediterranean storms that hit Greece every year. With wind speeds reaching over 60 miles an hour, the canopy had the potential to act like a giant wing and be ripped off the building. The engineers had to come up with a solution. They decided to make the roof so it behaves like a spoiler on a car, creating downforce when it's caught by the wind. So instead of lifting, it pushes down onto the supporting pillars. To test it out, they built a model to see how the wind would affect the roof. Its aerodynamic shape could survive the powerful storms. They then had to find a material that was strong enough to span the huge distance and cope with the force of the wind. They chose ferrocement.
Ferrocement has been used extensively in boat building. So tankers were built from ferrocement in the 70s. And also it was used as cladding material for very elaborate buildings.
Ferrocement is made of a fine wire mesh with a thin layer of concrete. It was first invented in the 1840s in France and is thought to be the first ever reinforced concrete.
Ferrocement confounds our expectations about what concrete can be used for. This is concrete that is thin and delicate and light.
Ferrocement can be made much thinner and outperform traditional reinforced concrete. But that requires an exact combination of cement and reinforcement.
We needed to go through very extensive testing for the ferrocement.
When tested, the 5-centimeter thick panels were able to support nearly 1,000 tons of force per square foot, the weight of 6 blue whales.
This thin mesh of 1 millimeter diameter is not produced normally as a structural material, it's produced as a fence.
The ferrocement was thin enough to keep down the weight of the structure and strong enough to span 100 meters in each direction. The next problem was that the downforce of the canopy in high winds would be enough to push the supporting columns through the roof underneath. The engineers came up with a radical solution: to build the canopy its own suspension system.
Above us and below us is ferrocement. Now we can see it, the whole structure with the ribs, and we are seeing the suspension system of the canopy from the column.
Instead of sitting on the columns, the canopy sits on the suspension system, which absorbs downforce even in heavy storms.
The columns enter the canopy, and then it is suspended with a system of springs and dampers from the column. So it's hanging from the columns. Additionally, we have vertical brakes that don't allow the canopy to move for small winds. It only moves for large winds. The whole canopy has an ability to move 15 to 20 centimeters. This movement will only happen in a hurricane, once or twice per year. This is the actual frequency that we have vibrations of the canopy. To have the actual vertical load, 100% of it being suspended from springs, to my knowledge, it's the first application in the world.
The canopy isn't only for decoration. Its 5,700 solar panels generate over 2 gigawatts of electricity a year, enough to power 1.4 million houses for an hour, and most of what the entire complex needs.
This building is designed to be sleek and stylish, full of tech, really heavily engineered. It's a fantastic piece of engineering.
The SNFCC took 4 years to build, opening its doors to the public in 2016. The building is not only a testament to how modern engineering can realize the impossible, but built at a time of crisis in Greece, it gave hope to Athens and a modern focus to the city's history and heritage.
The SNFCC is for everybody, and it's a real gift to Athens.
This building has completely transformed the whole area of Athens. It has become a point of attraction for all Athenians. Not only Athenians, for all Greeks.
I think this is one of the most important things, if not the most important thing that has happened in Greece the last few years. And I'm very proud that I was part of it and very fortunate.
Named one of the world's most beautiful cities, modern Singapore certainly has some incredible buildings, but it also has some of the cleverest. Like the Hive, built for the Nanyang Technical University.
University buildings haven't really changed since the 16th century. Boxy buildings, teacher in the front, children sitting quietly.
It not only looks eye-popping, but has a revolutionary design. Classrooms with no corners, and a building that gets wider as it gets taller to create an eco-cooling system capable of combating the hot and humid Singapore climate, creating a building for the 21st century and beyond. Kam Chan Hin wanted a building custom-made to teach the next generation of students.
This building is very much designed for the millennials. The new generation of learners, they like to explore, they like to participate, and they go for quick images. The mobile phone is a good example. We felt that a building of this kind actually encourages students to speak up, to challenge assumptions, to talk to one another, and to learn from one another.
Heatherwick studio architect Matt Cash took up the challenge.
No corners. No corners, okay. Why no corners? And the idea being is that in a way, corners are defendable. Kind of, you can get your back to a corner and you're kind of like this. And it sets up a kind of a dynamic in the classroom between, again, the kind of the lecturer or the master and the pupils. And they didn't want to do that, they wanted it in the round. And it's if you meet at a round table, there's no hierarchy there. But a round table is completely democratic.
The innovations didn't stop there, because the university also wanted the Hive to be one of the most ecologically friendly buildings in the city.
We have an overall target to reduce energy consumption by 30%.
The only way to do that was to get rid of traditional air conditioning.
When we're thinking about the geometry of the building, we're thinking about how do you cool that environment in the best way possible, not using too much energy.
With a single room, we can air condition it. When we get to the scale of big buildings, though, it starts to get expensive and it's a massive drain on energy and resources. It's not eco, and we don't like it.
So the Hive came with two monumental challenges: to engineer a building without a corner in sight, and to keep it cool in one of the most humid cities in the world without air conditioning. Matt and the team got to work reinventing how a university works.
So we started with one classroom, which is in effect a kind of an oval shape. And then we took that one classroom and we arrayed it, we clustered it around a central atrium. And in a way, that clustering created the coming together. So each of the classrooms arrayed around a central space, and then they stagger up and climb. It's about, in a way, increasing student interactivity. That was really the beginning of the idea and the beginning of the form.
The Hive is made up of 12 8-story high towers that slowly creep outwards from the base of the building. Incorporating these circular classrooms had drastically changed the shape of the structure.
You've got a building that's getting wider and wider before it goes in again. It's much like a barrel that wants to fall outward.
Building towers that get wider was far from easy.
Whenever you have anything leaning or at an angle, then it wants to move sideways, and there's that sideways force that also has to be resisted and carried on down to the ground. The consequences of not considering the stability correctly at all stages can be quite severe.
The engineers tilted the columns to work with the unusual shape of the building. letting them carry the weight of the floors above straight down to the ground below in one continuous motion.
The building kind of progressively steps out, so each floor is slightly cantilevered out from the next one. Now, when you're doing that with two kind of curving columns like that, the building wants to fall over. As the levels step up, at every level we have a ring beam, which is almost like in a barrel, where you have horizontal things that ties the barrel together. It stops the columns falling out, and that ties the whole structure together.
You don't often see leaning columns like that. It kind of goes against everything we think engineering should be. Straight up and down, solid, robust.
They may have overcome getting rid of the corners. Now they had to work out how to keep it cool.
Part of our challenge really was about the environment in Singapore. It's a very hot, humid environment. How do you cool that environment? And one way of doing that is to create an atrium in the middle. And atriums work by hot air, which hot air rises, rising up the middle, and then that drags air with it and creates almost like a chimney. And that chimney draws all the hot air up and away from the building. So the geometry was generated by trying to kind of cool the middle.
This is a form of passive cooling, which uses the form of the building to block, sink, and dissipate heat in a natural way. And it's a great way of really reducing the energy consumption, which is really important in somewhere hot and humid like Singapore.
The shape of the building draws hot air up and out of the roof. The constant flow of air cools it, and the hive's plants provide added shade, protecting the building from the sun.
The plants inside the building help to lower the temperature in the hall.
This building is totally energy efficient. It's been given the Platinum Mark for excellence in energy sustainability.
Matt had met the challenges set by the university, but he didn't stop there. He wanted a building that stood out.
We didn't have enough money to have a lot of different finishes. And so in effect, the floor, the walls, the cladding of the outside of the building is all concrete. People are expecting concrete to be grey, and that's the cheapest way of doing it. And if you had just a big grey building, it wouldn't have the kind of texture and relief that you would want. And so we experimented with lots of different ways of playing with concrete, treating it in a way like wet clay. On the cladding of the building, we use something called a retarder, which is, in effect, something that prevents the concrete drying at the same speed. And if the concrete's drying at different speeds, then some of it's hard and some of it's still wet, and then you wash that off. So some of the concrete exposes the stone, the aggregate inside the concrete, and some, the top surface, just a concrete finish. Having that variety means your eye kind of enjoys exploring it. And I think rather than understanding the building immediately, it kind of demands you look at it closer.
Although it's a radical design, the building's already won the hearts of the community.
It's called the Dim Sum building by some locals. That is because the shape also resembles the tiffin trays that are used to serve the dim sum.
It's obviously a really beautiful structure. It'd be a great and interesting place to work.
From what we know, the students actually love the place. Of course, it's very iconic. It's become a bit of a tourist spot. We're very proud of it.
The Hive created an environment that challenged the idea of how a university should work, and succeeded beyond all expectations, showing how engineering isn't only about keeping a building standing, it's about changing what's possible. How did engineering innovation allow a bridge to span this vast valley and become the tallest in the world?
Defying gravity, defying nature.
How did engineers rip up the rulebook to build this hotel upside down in an abandoned quarry?
When a building is flipped like this, then things that you would normally take for granted need to be completely reconsidered.
And what happens when you attempt a world first to build a forest in the sky in the middle of a city?
That is a huge amount of extra weight that the building needs to absorb.
This is the age of the extraordinary.
Where else can you swim from one skyscraper to the other 300 feet in the air?
Where ingenious engineers have unleashed unchecked creativity.
Everything in this building pushes at the boundaries of what's possible.
Building structures so outrageous, they defy logic.
The forces on this thing look like it should be torn apart.
Now, their secrets revealed. Discovering the incredible stories of their construction.
These are extraordinary feats of engineering.
To try and understand, how did they build that? What happens when a road that carries up to 50,000 cars a day needs to cross a river?
Crossing over a road, river, or valley? That's easy. Build a bridge.
But what if that river is in a valley that's 300 meters deep, 2.5 kilometers wide, and happens to be in one of France's most beautifully unspoilt regions? The answer is to hire one of the world's most visionary architects and assemble a team of brilliant engineers to construct the most advanced bridge possible.
You know something is at the cutting edge of engineering if you have to design a brand new system to deal with it.
The Millau Viaduct is the tallest structure in France and the tallest bridge in the world.
Nothing has been done exactly like this. Each big bridge is a new bridge.
It cost 300 million euros and took 15 years to create a bridge so special that people traveled from around the world to see it. So, how did they build it? It's quiet now, but in the late 1990s, the sleepy town of Millau in the south of France was a snarled-up bottleneck on the old tourist road from Paris to the Mediterranean coast.
Imagine peak holiday, the route from Paris to the Mediterranean, and the traffic just slows down. You've got 20-mile nose-to-tail pollution.
Relief, though, was on its way in the shape of a new auto route to the Med that 240 kilometers south of Paris would finally bypass long-suffering Millau. But there was no way around the massive Tarn Valley where the town lies. The valley is a vast, steep-sided, 2.5-kilometer wide split in the Massif Central plateau. Deciding exactly how to cross it wasn't easy. Michel Villager was on the project right from the first planning stages in the late 1980s.
The first idea was to go slightly down in the valley and to come up. And finally, somebody, a road engineer, said us, but why do you go down in the valley? We could not answer. And so we said immediately, we look at it.
So architects were asked to design a bridge to span the whole valley. And in 1996, the plan from Foster & Partners won approval.
Our interpretation as a team was to march across the valley from plateau to plateau with the most efficient, the lightest impact on the landscape, and create a series of spans. And along the way, you would bridge over the Tarn.
Building such an extraordinary bridge would turn the project into a laboratory of engineering innovation on a massive scale. The whole bridge weighs 290,000 tons and is made up of 3 major components. 7 giant concrete piers rise up from the valley floor, on which rests a 2,460-meter-long road deck. To top it off, 7 huge pylons tower above the piers, with tensioned cables supporting the road below. Because these cables send the load directly back to the pylons, which are balanced by an equal load from the opposite side, the cable-stayed bridge design is very efficient. To realize the slimline, elegant design would take innovation at every stage of construction.
That demands a feat of engineering on a completely different level, something extraordinary.
At the start of construction in 2001, the first things to be built were the 7 huge load-bearing towers, or piers. Building a road deck at this height had never been attempted before. They were so tall that the engineers had to turn to skyscraper technology. The builders used a technique known as climbing formwork. Each pier had its own platform and mold, which would create a 4-meter section at a time. Once the concrete had been poured and set, hydraulic jacks pushed the mold up so that the next level could be poured. But as the piers grew, getting the concrete up to the top to pour became more and more difficult.
That's where cranes come in. But the piers were so high that the cranes had to be tied to them for stability.
With robot-like efficiency, all 7 piers grew 4 meters every 3 days. They took 21 months to reach road level, by which point each contained 16,000 tons of steel and 85,000 cubic meters of concrete. Next came the road. 8 steel sections were assembled on site at the valley's edge, but lifting them into position with the crane at this height would be too dangerous. Incredibly, despite weighing 36,000 tons, these sections would be slid out across the top of the piers. But this posed a serious problem.
If you use a classical technique, you will have to push the piers, and in addition you have friction. And so the piers would not have resisted these forces because they are very tall.
The friction caused by sliding the sections of road over the piers could cause them to fall over. But the team came up with an ingenious solution.
So the idea was to develop a launching system which do not introduce any horizontal force on the piers.
What they used to lay the bridge deck of the Millau Viaduct was a complete one-off.
The team constructed 7 temporary metal piers. On top of all of the piers, computer-controlled hydraulic platforms would lift and move each road deck along very slowly out towards the center, with the middle road decks already rigged with 2 pylons. Launched from both sides, the road decks moved just 600 millimeters every 4 minutes, 5 times slower than a snail, until they met in the middle.
Each piece would move forward inches at a time. It took days to get the whole thing into place.
With each deck taking up to 3 days to reach its final position, this process was very vulnerable to one of the region's most unpredictable threats. Winds in the Tarn Valley have been recorded at 200 kilometers per hour, but even much lighter winds would cause problems during the critical deck launches.
Every morning, the site receives the weather prediction, and we decide not to launch if we have not 5 days in front of us with less than these 37 kilometers per hour.
Can you imagine what would happen if a giant piece of this road deck got caught up by the wind? And it would cause really bad damage.
Working around the clock for 2 days, the central sections, complete with the 2 middle pylons, were finally within touching distance. Global positioning systems had been used to plot their path. Despite starting at different heights and with a gentle curve throughout the 2.5 kilometers, when the roads met, they were within the 1 centimeter tolerance. The final component was not entirely crucial to the engineering, but was a fitting way to celebrate an incredible piece of innovation.
It was inventing how you would make the bridge, and that magic moment when, you know, from 1.25 kilometers coming together, that 2.5 kilometer, and they magically touch.
The road was complete, but it wasn't designed to solely rest on the 7 piers. It needed to be supported at much more regular intervals to be strong and rigid enough to take the loads of the bridge deck and 5 million vehicles a year traveling across it. This would be done by massive cables.
The Millau Viaduct is what we call a cable-stayed bridge. It makes use of thick steel cables to support the weight of the bridge and lock the structure together at the same time.
The cables would be hung from 87-meter-tall pylons, each on top of a concrete pier. The prefabricated steel pylons weighing 700 tons had to be installed in one piece. Loaded onto massive transporters which crawled across the bridge, the pylons were then inserted into a frame and pivoted into position. The 7 pylons would share the job of supporting their own 5,000-ton section of road, each from just 22 tensioned steel cables. Expected to have a lifespan of at least 120 years, the bridge needed to be easily maintained. So a secret tunnel was built in, running under the road. Camille Baudel is a tour guide.
We are inside the deck of the Millau Viaduct, and we are just underneath the roadway joint. That's why we can hear the noise of the vehicles passing on it. And the joints are here to absorb the movements of the deck, because when it's very hot, the deck expands, and when it's cold, it's retracted like this. So the joints are here to open and close all the time.
Being a road bridge, accidents have to be considered, especially a crash that causes a sudden weight imbalance, which could be catastrophic.
So these balls are here because if there is an accident on the traffic and a lot of liquid pours into the deck, these balls will float, so the liquid can go down and there is no more weight inside the deck.
Finally, in December 2004, 1 month ahead of schedule, the first cars rolled across this stunning strip of tarmac. Now 5 million vehicles pass over it a year, and people even take detours just to experience its magic.
Initially, you couldn't cross because everybody was stopping their cars and photographing. Because a lot of people make the journey just to see the bridge, as well as to enjoy the speed of the crossing.
The Millau Viaduct pioneered new ways of building and did it in record time. A remarkable achievement for a proud team.
A 3-year adventure for 500 people. Everybody coming from different disciplines, different backgrounds, and wanting to achieve something that was truly outstanding, something that had not been done before, and something that would turn making a car journey, a truck journey across this 2.5 kilometers in the sky, kind of ethereal experience.
Each bridge is a prototype. You use ideas which generally already exist. An engineer must know what was done before and must be able to reuse the good ideas which exist. A colleague said, engineers are climbing on each of our shoulders.
Most buildings in Shanghai try to reach for the skies. But just a few kilometers west, designers and engineers have flipped this habit on its head. Here, they have gone down, down, down. Nestled into a 90-meter deep quarry is an incredible new building that offers a true escape from reality.
This place is part Thunderbirds, part Bond villain lair. It's even got a shark pool.
But this is no film set. It's the world's first underground hotel. Creating this 49,000 square meter upside-down hotel with underwater floors meant turning engineering on its head.
When your building's flipped like this, everything that you take for granted is just thrown into the air.
It took 12 years and $300 million to engineer a way around earthquakes, floods, and crumbling rock. But the result is a world first. The 336-room subterranean Wonderland Hotel. So how did they build it? Back in 2005, before the project started, this disused quarry, a 30-minute drive from Shanghai, was earmarked to become the exact opposite of a tourist destination.
The government planned to make this place as the treatment place for the garbage.
But a developer had a vision to create a hotel with a feature so unique that people would travel from around the world to experience it. Tasked with turning this site from garbage can to gold mine was architect Martin Jochman.
When I faced the quarry, actually it was completely overgrown and the water level was quite high. It was more like a lake, which was surrounded by old industrial buildings and overgrown vegetation.
Martin used the location's natural assets as a starting point for his design.
The inspiration for the design came from the quarry and from the greenery, from the rocks, from the waterfalls. And it needed to span between the ground level and the bottom of the quarry itself. This was what would make it really outstanding and spectacular.
Martin was keen to create a building that fitted naturally and seamlessly into the environment. What appears to be just a 2-story grass-covered complex at ground level is only the tip of the structural iceberg. Hidden below is the main 16-story hotel room section of the building. The design embracing shapes from within the quarry. One half curves out, the other curves in. Between them is a waterfall-like glass atrium, which houses the elevator shafts and services. But it's at water level where things are most unusual. Here, huge 5-meter-deep aquariums hold over 300 tons of water, meaning the lowest 2 floors of restaurants and guest suites have huge windows onto an extraordinary underwater world.
What I tried to do is to create a building mass that joined with the quarry and became part of it. It became part of the overall character of the quarry itself.
In 2011, as the 5,000-strong construction team began work, this challenging site threw up its own unique set of problems. Before the engineers could start building the hotel, they had to prepare the quarry itself, which had been abandoned for years.
Before we start building construction, we have to make sure the condition is okay for building works. And as you see, the cliff here is not very stable, so we have to solve this problem.
So how do you prepare a giant hole filled with water for an underground hotel? First, the team drained the quarry of 10 meters of water before turning to the rock faces, which would need to fit the hotel structure.
The quarry had to follow the shape of the building itself. But also, because of the safety requirements, we needed to do some stabilization of the rock faces themselves. Some of the rock faces had to be blasted, but not too many.
The quarry is comprised of andesite, a type of rock formed during a volcanic eruption. It's solid in places, but can be crumbly and unstable, creating dangerous conditions for anyone below.
It is pretty amazing to see behind this building. because it looks from the outside as if it's all fixed to the wall. But actually, there's a huge cavernous space behind it, and it's really only fixed at the top and at the bottom.
The team came up with a solution. 15-meter steel bolts were driven deep into the rock at 2-meter intervals, creating a huge grid. The compressive force of these 6,000 bolts knit together the loose rock. For added security, a metal mesh was anchored across the bolts and sprayed with a thin layer of concrete. All this is still visible from the inner atrium.
It is pretty amazing to me how well the concrete has weathered to colour match the original walls over time.
Only once this was all done could they begin work on the massive foundations. They would require 60,000 cubic meters of concrete into which steel trusses would be embedded. But pumping all that concrete from ground level down 90 meters wasn't as easy as you might imagine.
Until it sets, concrete is a delicate mix of materials of different sizes and weights, and it has to be continually mixed.
Getting the concrete down was probably the most important and most difficult to solve. We all know how to pump concrete high to build skyscrapers, but pumping it down 90 meters is a different story altogether, because gravity can separate the parts of the concrete and can weaken the concrete.
On the journey down the chute, the size and weight of the different components that made up the concrete fell at different speeds, separating out by the time it reached the bottom of the quarry. So the team came up with a simple but incredibly effective solution to ensure that the concrete stayed mixed.
The builder had to create remixing stations on the way down the quarry, where the mix of the concrete would be collected, remixed, and sent down again, so that when the mix got to the bottom where it needed to get to, it was the right consistency.
This innovation was just one of the ideas pioneered as engineers tried to overcome the site's unique challenges.
This method was patented, so it's one of the, I think, 38 or so patents that the builder had to create to realize this building.
By 2015, the foundations and substructure were completed, and work had begun on the next levels. But the build faced another challenge. 7 years prior, the devastating Sichuan earthquake that left 87,000 dead and 5 million homeless prompted the Chinese government to enforce strict seismic building codes across the country.
But when you have an earthquake, then what's happening is that the ground is shaking violently from side to side, and it's that sideways force that has to be carried down into the foundations. So if a structure is in an earthquake zone, then it has to have a way to resist that sideways motion, or it will fall down.
To prevent a catastrophic collapse, buildings in earthquake zones are often set apart from the ground using isolator pads.
Base isolators are essentially like suspension, but for a whole building. This means that when the earth moves because of the earthquake, the base isolators absorb that movement, leaving the rest of the building completely undisturbed.
The Wonderland Hotel, though, couldn't use this technique in the traditional way, as it had a fundamental difference.
Normal buildings have one point of contact with the earth, at the bottom. Here you need to connect the top, where people enter, with the bottom, where the weight of the structure is. The problem is that during an earthquake, these might move in the opposite direction. And when that happens, well, you have a hotel falling in a hole.
To prevent the top of the building tearing away from the bottom during an earthquake, both ends of the structure needed to move independently of each other. So a radical solution was needed. First, a series of inverted L-shaped steel trusses were embedded in the concrete base that is rooted to the quarry floor. This creates a rigid joint at the bottom of the building that reduces the lateral movement of it during a quake. It was in fact at the top of the building where traditional isolator pads would be used.
The worst case scenario, if it was fully rigid, would be that the whole building collapses, and it's a major disaster. The way it's been designed was a rigid connection at the base, and then at the top had to sit quite loosely on the edge of the quarry so that it would enable any movement in case of earthquake.
So the engineers turned seismic isolation technology upside down.
They've used a form of seismic isolation, which means they've taken that top section, they've sat it on a series of separation joints, steel plates, which means that the sections can move independently.
16 floors up at the top, the building isn't fixed onto the rock. Instead, the upside-down L-shaped trusses of the structure rest on the concrete lip that runs around the quarry wall. A set of steel isolators sit between the trusses and the lip, allowing the building to slide back and forth in the event of an earthquake.
This is to allow for minimal damage to the building rather than the whole building collapsing.
Water was key to the design of this complex. And in 2018, one of the last phases of construction was refilling the quarry with over 200 million litres of water. It would take 6 months, but would also pose one of the biggest threats to the hotel and its guests: flooding.
You've got twice the annual rainfall of London coming down into a waterproof rock hole. Plus, there's a waterfall pouring water in, and a river, and a canal, all within overflowing distance.
Prone to typhoons and monsoons, this coastal region is one of the world's most vulnerable to flooding. So the team came up with a solution that could instantly address the smallest increase in water.
In order to maintain this water level, we have a very powerful emergency pump, and this will come into operation if there's too much water coming into the quarry. It could be through exceptional rainfall, or if there's some breakage into the quarry from the canal. So this can then deal with that situation.
Fully automated and computer controlled, the emergency water pumping system is programmed to keep the water level within a 500 millimeter tolerance. 6 pumps are at the ready to evacuate 800 cubic meters per hour into the surrounding canals. The next challenge was to create a suitable ecosystem for exotic fish like these. The 2 underwater floors needed to have spectacular views to warrant the $3,000 a night price tag for these exclusive suites. But the quarry lake was too dark and vast to guarantee guests a glimpse of Jaws' little brothers.
The client envisaged that their part of the building would be underwater, but no real instructions as to how to deal with it. So I suggested that we put aquariums below the water level to face the guest rooms or the restaurants. So the client really agreed that we should put themed tropical aquaria with some sharks in it as well.
Separate from the main body of water in the quarry, these self-contained aquariums would be huge. 5 meters long and over 5 meters deep, containing 40 tons of water. The engineers needed a material that would be strong enough to withstand the pressure of the water and clear enough for the guests to see the display. Normal glass wasn't up to the job.
Glass is perfect for small aquariums, but when you're trying to hold back many tons of water like you are here, then it's just too brittle, meaning that a small crack could be catastrophic.
Upping the depth of the glass was pointless. The thicker the glass, the more opaque it becomes. The solution was to use acrylic.
Acrylic can be as thick as 200 millimeters, 300 millimeters, and you can still see clearly through it.
The largest of the acrylic aquarium windows the engineers installed weighed over 4 tons, but revealed the underwater idyll in all its glory. In 2018, the Intercontinental Wonderland Hotel finally opened its doors to the public. It had taken 12 years of hard graft and amazing engineering to overcome an array of complex problems. But against the odds, Martin and his team created this extraordinary building, the world's first underground luxury hotel, an outstanding achievement for a site once earmarked for the rubbish heap.
This project is an example of taking a scarred piece of land and turning it into something beautiful, luxurious, and even natural. But above all, it's an amazing piece of engineering.
Cities are growing more crowded by the day. Greenery is being pushed back to make room for concrete. But what if it didn't have to be that way? In Italy, radical designers and engineers are pioneering a new approach to both urban expansion and environmental regeneration.
This idea was a bit crazy, like having trees on a building.
These trailblazers have rethought how city life could be, lifting a forest into the sky, creating a stunning, life-giving sculpture.
It feels like this futuristic version of what buildings should be.
What many of our cities and urban areas are crying out for is more green space. This could be the solution.
Engineers had to create a structure strong enough to hold a hectare of forest and tough enough to withstand high winds, all while battling vibrations from subway trains. So how did they build it? Milan is a city of 70 square miles. Almost all of it, dense urban sprawl. But packing people in has meant sacrificing something important.
Green spaces are an essential part of the city's ecosystem. Not only do they do the obvious thing of absorbing carbon dioxide and emitting oxygen, but they give us humidity, they collect dust, and create an ecosystem for insects and animal life. All of these things together make the city a more hospitable and pleasurable place.
Starved of the space to create a traditional garden, a developer decided to think outside the box.
Developers love challenges. So the big theme was how can we reintegrate the neighborhood into the city, and having the opportunity to do it through the nature. There was a strong commitment by all of us in making a sustainable project.
The answer was to create a building that could hold all the plants of a park on the ground within a vertical structure. This would be Bosco Verticale, or the vertical forest. Structural engineer Luca Buzzoni was brought in to make it possible.
As a structural engineer, I must admit I was skeptical about it. You typically don't put big trees on tall buildings because of additional weight, because of wind forces, and those sort of things.
Luca's doubts were well-founded. No building like this had ever been attempted. On these structures, plants came first, and they would impact the way the buildings were constructed, so an unusual collaborator was needed. Laura Gatti is an agronomist, or in layman's terms, a plant whisperer.
This building has been designed for trees. We make calculation on what the trees is needing to survive, thinking to be a tree and thinking like a tree. This is not a building in which the greening is put just for decoration.
Normally, the landscaping is the last part of the project, but here the plants are actually built into the fabric of the structure, and the design of the structure is led by the needs of the plants. That's pretty standard for a greenhouse or an arboretum, but it's not that usual for an inner-city block of flats.
This unusual brief for up to 27-story apartments that were half giant plant pots would result in a unique and complex plan. The ambitious design called for 2 residential towers that would rise 110 meters and 76 meters from the ground. Cantilevered terraces would extend 3.5 meters from the structures. These would have to be strong enough to hold 900 trees and allow them to grow up to 6 meters in height. In addition, 16,000 other plants would act as cladding for the building. Construction began in 2009, with 6,000 workers on site. Their first challenge came from Milan's public transport system.
The buildings on this project have been built either on top or very close to existing metro tunnels. So it was quite a challenge to build big buildings on top of those tunnels.
27-story buildings like these would normally need concrete piles drilled deep down into bedrock for stability. But with the subway carrying 1.4 million commuters every day right underneath, the engineers had to find a way to give their buildings a strong base without touching the tunnels. And they inadvertently struck gold.
It was possible to design shallow foundations even if the buildings are pretty tall and pretty big, because the soil in this part of the town is very good. It's made of sand and gravel, so the capacity of the ground is pretty high.
Although the ceilings of the subway tunnels were as little as 3.5 meters below ground level, the engineers could cautiously build on top of them. During construction, a 24-hour monitoring station was set up to keep an eye on any stresses exerted on the tunnels below. So now the foundations wouldn't interfere with the subway, but the vibrations from the trains could still ruin the living conditions for the building's occupants. So the engineers turned to a solution often used to protect buildings in earthquake zones.
So basically what this system makes is very similar to what you have in a normal car with a shock absorber. So in the same way, shock absorbers take vibrations from the irregularities in the roads and damp them down.
The vast buildings were floated on a bed of base isolators made up of steel springs. The springs act as dampers for the vibrations from the trains, so the earth is free to move below the building while the structure remains insulated from the subway line underneath. With the building and trains effectively isolated from each other, the engineers could tackle the most unique challenge of this project. They had to design a structure to cope with the hundreds of plants and trees and the soil they live in, whose weight and size constantly change. To complicate things, many of these plants would live around the edges of huge cantilevered balconies. Cantilevers are a trick of engineering. These reinforced concrete slabs look like they're suspended in space, when they are in fact internally fixed to support columns within the main structure. But they are usually designed to bear a limited weight.
So when I think about these balconies, I think about the fact that they're essentially experiencing cantilever action. So not only is it carrying the weight of the plants in the soil, but any moisture that's in the air that gets trapped into the soil is just adding to the load and therefore increasing the amount of reaction that the attachment has to resist on the exterior of the building. And so the fluctuations of the loads or the weight on these balconies really does change as the seasons and the humidity changes.
The engineers came up with a way to make the balconies incredibly strong to counter the weight of the trees and plants.
We have post-tension slabs, and what that means is that in concrete slabs we normally only have steel rebars. In this case we also have steel cables, and those steel cables are pre-stressed so that the presence of the cables in the slabs provide additional resistance and additional stiffness.
So, as well as predictable, stable steel and concrete, these towers would also be shape-shifting organic structures with dynamic loads that needed to be understood and controlled as much as possible.
This is a live building. It changes season after season and it grows year after year. So it's not something normal on a project. So what we did, first of all, we tried to understand how to cope with the changing life of the buildings.
It was crucial the experts identified plants that gave the engineers a chance to design a building that could cope.
We select trees that are not allergenic or not messy tree, and we understand which are the position on the building in which the wind is higher than other parts, and we select the trees to thrive this condition.
That wind was the biggest concern. A large tree in a strong wind could put serious strain on the building, and the wrong trees could badly damage the structure. The team needed to know as much detail as possible before choosing these potentially destructive elements. A selection of trees were tested in a wind tunnel to assess if they were suitable for high-rise living.
First of all, we had a set of tests in the wind tunnel here in Milan to understand the behavior of the trees together with the behavior of the building, to see if the presence of the trees was introducing additional forces on the building and to understand the magnitude of the additional forces on the building. And then we had a second set of tests in Florida.
At Florida International University, they have built the wall of wind. Here, they can build whole buildings and blast them with hurricane-force wind to see how they stand up.
The tests helped to determine which trees were the perfect weight and shape for the building. But there was another, more basic worry that had to be addressed. If a small tree on the ground is knocked over by the wind, it can be a small problem. If a tree falls from a large building, then you've got a very big problem.
If a tree falls from the 27th floor, everyone is going to know about it.
With 2-meter trees planted 27 stories high, no one wanted to take any chances.
For most of the trees and all the medium and tall trees, we have cables that basically provide an additional anchor for the trees in case they break so that they cannot fall over during windstorms, for instance. And then for all the big trees, and especially for all the positions that we identified as possibly critical because of high wind velocity during windstorms, we provided an additional anchoring system that basically connecting the root ball of the trees to the concrete structure so that they cannot fall over.
It took 3 years to create this tower block oasis, which was officially opened in 2014. These 2 buildings are proof that people can have it all. Enjoy life in the metropolis and a taste of nature right outside their high-rise window.
I think it's also great that a person can look out their window and see what looks like a forest growing on their balcony when in fact they're in the middle of an urban area.
The engineers who built Bosco Verticale overcame new challenges and achieved the best of both worlds, pushing sustainable green spaces skyward, offering a glimpse of the future for city dwellers.
It's a brave example that shows that something different is possible, that healthier cities are possible for us.
The strong commitment and passion by all of us made a project that at the end has become today a symbol, an icon for sure.
How did a team of engineers nicknamed the Extreme Team build a futuristic research station in the world's most extreme climate?
It's a really savage environment for any building to endure. It's just really harsh out there. You have temperatures that go as low as -58 degrees Celsius, and then you have wind speeds that go as high as 160 kilometers per hour.
How does this stunning visual trick make a 3.5-ton concrete arch levitate?
It looks like the wing is floating completely unsupported.
And how did they build the world's first rotating boat lift, able to carry 500 tons of water and 2 boats over 20 meters into the air?
All the Falkirk wheel needs is the equivalent power of 8 boiling kettles.
This is the age of the extraordinary.
This house always is on the verge of falling down.
Where ingenious engineers have unleashed unchecked creativity.
Everything in this building pushes at the boundaries of what's possible.
Building structures so outrageous, they defy logic.
The forces on this thing look like it should be torn apart.
Now, their secrets revealed. Discovering the incredible stories of their construction.
These are extraordinary feats of engineering.
To try and understand, how did they build that? Imagine the engineering it takes to build an advanced scientific research center that can cope with outside temperatures of -50 degrees centigrade and house 60 people. It has to be completely self-sufficient for months on end and be able to move locations quickly when danger strikes.
It's a brutal environment for any building to survive in.
But that's the building the British Antarctic Survey needed. A mobile research station that could survive in the most hostile place on Earth, Antarctica. This ingenious series of rugged pods uses train and space shuttle technology so that top scientists can study our planet's atmosphere all year round. But designing something that could be built on a slab of ice 10,000 miles from home was a massive challenge.
The people who were building it had to actually use electrically heated gloves to counteract the frostbite.
The crippling cold was only one of the hurdles a dedicated team had to overcome to pull this off. Every part had to be delivered to an ice dock that could crack open at any moment. Snowdrifts would bury buildings and equipment in the blink of an eye. And the summer build season was so short, it would take 5 years to complete. The result was the extreme mobile research station called Halley 6. So how did they build it? For the last 65 years, Britain has been pioneering the scientific study of the Earth's atmosphere in the most extreme environment on Earth.
This place has 1.2 meters of snow a year, and the snow that does fall, it never melts. Then you have the drifts. This is a big, wide open space, so anything that you put there is going to gather a lot of snow on it.
Despite the tough conditions, the clean air and low light pollution are the reasons why the British Antarctic Survey has been building research stations in the Antarctic since 1956. In 1985, its scientists discovered a huge hole in the ozone layer, a finding that led to the global banning of CFCs, reversing a potential catastrophe. Named after the great astronomer Edmund Halley, the first 4 Halley bases were simple structures that worked for a while, but always ended up buried deep under the ice. In 1989, they upped their game, building the 5th base on adjustable stilts.
So Halley 5 was quite clever because it has these screw jacks, which meant the building could be jacked up every year by 1 meter or 1.5 meters to help it escape from the rising snow level.
So Halley 5 could move upwards to avoid the snow, but there was a bigger problem it couldn't escape. Every year, the ice shelf it's built on moves 400 meters closer to the sea.
The Halley 5's legs were fixed into the ice, and so they had to throw that design away because there was a risk that the ice could break off and the whole thing could just drift into the sea.
It was time for a new, better Halley research station. Architect Hugh Broughton rose to the challenge of designing a station that could overcome the difficulties of being built and operating in Antarctica. From the start, he faced an unusual set of limitations.
Everything that needs to be delivered to Halley, first of all, gets unloaded from a ship onto sea ice, and that the maximum weight of component could be no more than 9 tons. Then the other challenge is that this building needed to be relocatable between 15 to 20 kilometers, so quite a decent move.
Being able to move the station to avoid being stranded on an iceberg topped the already formidable design criteria. Some radical thinking was needed.
The first thing we decided is that we should come up with a modular solution. So break the requirements of the British Antarctic Survey's brief down into a series of interconnected buildings. And the reason we did that is that those buildings could be disconnected and moved more easily from one site to another.
The modular construction is really fitting for remote environments like this, much like the International Space Station, where you can put things together bit by bit without having to dig foundations or anything that you would traditionally see in a more reasonable environment.
The 8 pods, there's 2 sleeping pods, 2 science pods, 2 generator and plant pods, 1 command pod, and 1 double-height living pod.
Along with a team of expert engineers, the architects created a blueprint for what would be the most complete extreme environment accommodation ever built. 8 individual pods would be linked through enclosed gangways, like train carriages, to create one integrated living and working organism. To cope with the constantly rising snow, huge hydraulically adjustable legs would allow it to be raised and lowered, and each leg would sit on a massive Teflon-coated ski. If danger threatened, each module could be detached and moved to a new location where the station would be reconnected, avoiding a catastrophe. The modular plan solved many of the problems the extreme environment presented, but there was no getting away from the greatest single challenge facing its construction. The super short summer building season of just 12 weeks between December and February.
The construction season in the Antarctic is unbelievably short. Days in January and December, which might be -5, suddenly at the end of February, beginning of March, you're working at -25. And that's pretty hardcore if you're working outside. So then you've got to leave your site for the following 10 months until you can come back again.
While the construction crew could fly in on a Russian transport plane, all their tools and supplies had to be delivered by ship. The logistics here were tough enough, but it was that short 3-month window when external work was possible that meant a traditional approach to construction was impossible.
The only really sensible solution was to prefabricate everything in a warm country, in this case, South Africa.
To maximize efficiency, the engineers test-built 2 complete modules near Cape Town. This meant they could perfect components and train the construction team before shipping all the parts 7,000 kilometers to Antarctica.
The buildings were built is in a kind of kit form, and that's because it's hard to move things when the ship arrives at the edge of the sea ice.
The on-site build began in 2007, with icebreaker ships straightening part of the ice shelf edge enough to dock alongside. Once in position, everything was unloaded at breakneck speed. The planning had been meticulous.
We wanted to be able to unload components, for the components to be as big as possible within that weight restriction of 9 tons, and for all the parts to be able to click together as quickly as possible. The biggest part that we made was the steel frame which forms the base of each of the modules, which is basically a whole series of tubes joined together in a 3-dimensional form to maximize strength, making it easier to move from the ship to the building site.
For 7 days non-stop, Caterpillar tractors pulled 500 tons of cargo 12 kilometers inland to the still functioning Halley 5 base. The result was an extraordinary collection of prefabricated components awaiting assembly on the ice.
Everything was arranged in a very well organized, very well labeled line, 4 kilometers long.
The plan was to get each module on its legs and with all the key components fitted before winter arrived, shutting down the site until the following year. The construction crew of 40 men, who lived in prefabricated huts near Halley 5, worked in shifts around the clock to stay on schedule.
In order to maximise the efficiency of the construction process, we approached it in the same way almost that you would an assembly line for making a car or something like that. So we had one crew doing steel frames, another crew building shell.
Given the dangers of being in the Antarctic and the limitations on space, all of the builders had to be able to do more than one job.
There would be a team installing the primary building services, things like the generators, the sewage treatment, the water production unit, and then the service connections that go between the modules.
These are definitely no ordinary builders. In fact, they were nicknamed the Extreme Team.
Behind me is a second energy module with all the plant and equipment placed up on the floor deck. The obvious ones to point out are the big pink tank at the back, which is fuel, and the big grey tank at the front, which is water.
Every single unit that could be pre-built before arrival had been.
As you can see, there's the prefabricated bedrooms, plant room and WC. Next stage for this is to have the structural steelwork erected around it.
The bedrooms had the beds in, the desks in, the wardrobes. We didn't go as far as putting the duvets and the pillows on, but it was pretty close to that.
By the time the Extreme Team had the pod frames on their legs with the key components fixed inside, the days were becoming very cold and short. It was time to wrap the structures and prepare the site for the bitter winter to come. They could only hope the equipment and materials would survive.
So if you're going to leave any of your equipment there, you need to make sure that it's durable enough to withstand the harsh Antarctic winter. And that was a hard thing to do. There are materials which are used in food cold stores and things like that, but they typically go down to -25. But to say to someone, oh no, your product's actually going to go down to -55, that's sort of a different level.
In fact, it was discovered during testing off-site that the module cladding was too brittle. As a result, the following summer season, no work was done in the Antarctic, while the materials were perfected in South Africa. Finally, 21 months after wrapping them up, the Extreme Team returned and the half-built modules were released from winter's grip.
Okay, so here we are on the Halley 6 site. These structures are going to be towed up a ramp. The snow height here is about 20 foot at the back. So we'll clear it out, make a ramp, tow the structures out and take them to the south.
Cladding the modules was next. It was these improved panels that would give the Halley 6 pods their distinctive shape. A look inspired by a 50-year-old kids' TV series.
I can totally see this in the design, but apparently the architects and the engineers for this project were inspired by the 60s puppet show Thunderbirds.
I was a massive fan of the Thunderbirds. I think the influence is pretty clear. You know, Thunderbird 2 was coursing through the design from day one.
The Thunderbirds-inspired pods wouldn't just look good. Crucially, they would be the first line of defense against the harsh weather for everything and everyone inside.
The walls are made of glass-reinforced polymer, or GRP, and more commonly known as fiberglass. It's 75% lighter than the steel equivalent, and it's super strong, and it's lightweight, and it can actually resist corrosion. And best of all, it's a brilliant insulator.
Although fiberglass was known to be tough, Hugh needed to be sure it would survive the Antarctic conditions.
When we were having the glass fibre shell manufactured, we went through a really rigorous process of testing. We subjected it to the effects of the ice being blown in the wind, so we blasted it with sand to simulate that. We sprayed water at the cladding material or the building shell material, and then lowered the temperature really quickly to see what happens under freeze-thaw kind of cycles.
The glass fibre cladding, backed by 30 centimetres of high-performance insulation, would protect the researchers from the cold. But there is another extreme that people here need protection from, and that's the light, or lack of it.
We decided that at the heart of the station, in the main big red social module, it'd be really great if we could have a big double-height space with a big window, because you just get really nice light in the Antarctic in the summer, and it would just provide a really great social focus for the community. But of course, the big challenge you have in the Antarctic is if you create a big window, then it's also a source of massive heat loss, potentially. So we really searched high and wide around and discovered this incredible material that was invented by NASA called nanogel.
Nanogel was used on the Space Shuttle nose cone to protect it from the extreme heat of re-entry, but is equally effective at protecting from extreme cold. It also happens to be translucent.
Around 50% of light is actually transmitted through this material, so we have this big window at the heart of the station which allows lots of good natural light in without letting lots of heat out of the building.
With 400 metres of the ice shelf flowing out into the sea every year, by December 2011, the third season of the build, it was time to tow the modules 15 kilometres inland from Halley 5 and the ever-approaching edge. But by now, with modules fully built, even the smaller blue pods weighed as much as 100 tonnes.
The biggest challenge to getting the pods to their new home over the last 15 kilometres was overcoming something called stiction. This is the static friction that needs to be overcome to get objects to move.
The designers turned to a very common material found in almost every kitchen.
The skis are made out of high-grade steel that's suitable for a cold environment, and then they have a layer of Teflon, which is essentially fixed to the underside to help them to glide across the ice.
The skis were so effective, the extreme team had to make sure the 100-ton pods didn't run out of control.
H2, last night it was pulled off the construction line at this end, turned around, and a few tests done on it. What we're interested in is how slowly can we tow it, so how easily we can control it, and how quickly we can stop it, or what the stopping distances are. Because when you get to the other end, it will have to be a certain distance apart.
Being twice the size of the blue modules, moving the big red command module presented a much bigger challenge.
We're definitely over 200 tonnes with it, so just out of our comfort zone slightly. But good team on the job. If anybody can shift it, we can.
Moving the 8 modules the 15 kilometers took days. And as each module arrived to meet its new next-door neighbor, they were introduced with a bang. Fortunately, the connecting gangways were tried and tested super tough components.
They connected the pods using a double-layered version of the kind of concertina connections that you see in many railway carriages.
They're insulated when they're used in the Scandinavian countries. So again, it's normally used in the rail industry, but we just transferred it over to our buildings.
Finally, all 8 modules were linked and sealed from the weather. The only exterior connection, one safety gantry, an intentional fire break to protect one set of modules from the other in the event of a catastrophic fire or explosion. The last job of the year was to prepare Halley 6 for the next blast of winter.
Because the snow level is constantly rising, what you do is that each leg in turn, you lift it up using the hydraulics, you push snow underneath to make a platform of around 1 to 1.5 meters. And when you've done all of the legs, you then use the hydraulics again to jack the building up so it's sitting on these snow platforms well above the surrounding ice level. And then when it snows and the wind blows snow around over the winter and the level rises by 1.5 meters, it brings the whole thing kind of up to a level again.
In February 2012, over 5 years after the build began, Halley 6 came into service as the British Antarctic Survey's new research base. Its 60 occupants had never known such luxury.
If you're going to do research and you're going to live in one of the coldest places, if not the coldest place on Earth, then the least you can do is have a really cool place to chill in.
Halley 6 is without doubt the most complete extreme environment accommodation ever built. But in the Antarctic, Mother Nature takes no prisoners. In 2016, a huge new 150-meter deep crack appeared in the ice shelf. Just 30 kilometers from Halley and moving fast, it posed a grave risk to the station and the team.
This crack was discovered on the 31st of October 2016, so it's known as the Halloween crack, and it was moving at some speed. And so they then took the decision that because there was one crack going in one direction and another at 90 degrees, that the new site for Halley 6 had become far more dynamic than they had originally envisaged, and there was risk of leaving people over a winter of not knowing how those two cracks would interact.
They decided to act. It was time to test out Halley 6's built-in mobility and move the base to safety and a new site inland. It was a timely reminder of how brilliant engineering and design can make the impossible possible.
Somebody living in an Antarctic research station, their life is at risk constantly because of the extreme environment. So you need to think of every single situation. Building a research station in the Antarctic is equivalent to building a Formula One racing car. You just can't leave anything to chance. There are a number of parameters that you have to design within, and you have to give each of them a great deal of respect, because failure to do so will be catastrophic.
(9,500 kilometers north of the Antarctic Circle, just off the coast of Morocco, are the Canary Islands. With year-round sunshine and warmth, buildings here have no need to protect their occupants from harsh weather. Instead, they can be built purely to celebrate their surroundings and purpose. Which is exactly what this incredible concert hall was built to do. Its 130-meter-long, 3,500-ton arch is engineered to hover above the Auditorium below.
It's an incredible optical illusion. It looks like the wing is floating completely unsupported.
It's the improbable made to look impossible.
Inside is a stunning space for over 2,000 music lovers. But it's outside where the building hits the high notes. The incredible 58-meter-tall arch is only possible thanks to a secret skeleton of hardcore steel. The concrete cladding that creates its skin was so pioneering, an extraordinary new machine had to be custom-built to make it. Curved walls glisten with over 3 million tiny handmade tiles, and the giant wing flexes in the powerful wind. Auditorium de Tenerife is a stunning engineering performance. So how did they build it? In 1997, work began on a new concert hall in Santa Cruz de Tenerife in the Canary Islands. Spanish modernist architect Santiago Calatrava, who'd recently finished the awesome Oculus Transport Hub in New York's Trade Center, had designed a building that could match any music venue in the world for visual drama, both inside and out. His design of flowing forms performing impossible engineering gymnastics all clad in seamless concrete, would be one of the greatest construction challenges of its time. The most difficult to build would be the 3 curved components at the heart of the structure. Each would have a nickname. The nut would be the 45-meter-high central building to house the 2 performance auditoriums. It would also provide a single point of crucial support. The nut would be flanked by the 2 sails. These curving slabs are actually the outer walls of the main concert hall. On top is the wing. This massive structure, weighing the same as 10 747 aircraft, would be made of a steel frame clad in a thin layer of very ingeniously cast concrete. It would rest on that small point of support provided by the nut.
To create a structure like this, there is no off-the-shelf solution. You have to create something entirely from scratch.
The bespoke building technique that was key to the creation of Auditorio was the concrete formwork that created its cladding.
The simplest form would be to take 2 wooden boards, support them in place, put reinforced concrete in the gap in between, fill it all with concrete, let it set, and take the boards away and you've got a board.
Concrete formwork can be used like blocks to build walls. One layer added on top of another as many times as the steel reinforcing inside allows. Stacking layers like this is how engineers virtually hand-built the huge concrete walls of the sails. But the massive tapering, arcing wing would present a completely different challenge and a solution that was a world first. By 2001, the nut and sails were structurally complete. It was time to build the giant wing. Like the sails, the surface of the wing would be concrete formwork, but hidden inside would be the heavy-duty engineering that made this outrageous shape possible. A huge steel framework was prefabricated in Spain and shipped in 17 pieces before being assembled into larger sections on site. Juan Carlos was the site engineer.
Each piece weighed around 200 to 250 tons. They were lifted with a crane, and once they were up, a system put together the mobile and the fixed part, welded it, and then let it go. It's unique.
You have a steel skeleton that was constructed to give the whole thing a rigidity and strength. 24 rows of beams.
Once the steel frame of the wing was assembled, scaffolding was built under the inner areas to support traditional wooden formwork molds. But using formwork to make the concrete outer shell on the huge areas of the wing was not an option. Mainly because using the scaffolding required to work at such heights and difficult angles would have been impossibly slow, complex, and expensive. These problems meant the construction company had to come up with something special.
With the wing, the big curve, this was such a complex process of engineering that they had to design a special machine to put the iron and the concrete in, and this was supported by the same steel wing. It's unique and was built especially to do that.
This machine is called a carriage crane. It was assembled on the back of the wing, and its huge arms wrapped around and underneath to support the formwork. Adjustable in every direction and guided on huge rails, it enabled concrete to be attached along the wing in previously unreachable places.
This was a very slow process to create the wing. They had to align the formwork, pour the concrete, let the concrete set, then move the machine up and realign the formwork in a different, narrower shape and a different angle, and then re-pour the concrete and let it set and repeat that 32 times.
The final result is an extraordinarily fluid shape that, despite weighing 3,500 tons, appears to levitate.
This is an amazing optical illusion because when you look at it, it just looks like this wing is just completely floating in space. But from certain angles, you can see behind the smoke and mirrors.
The wing is supported at just 5 points. An amazing feat considering the powerful winds that almost constantly sweep across the Canary Islands. But one of these supports is a special steel shock-absorbing tube that moves up and down with the wing to stop it from tearing itself off the building.
In really high winds, you can hear it just bouncing up and down, which I'm sure sounds pretty terrifying, but I'm sure they knew what they were doing.
The Auditorio's architect, Calatrava, wasn't satisfied with just making the concrete achieve impossible shapes. He wanted his building to have an outstanding surface too. The concrete was mixed with a high proportion of sand and titanium dioxide to brighten it almost to white. But Calatrava wanted more. To make the building gleam, he wanted it covered in 3.5 million tiles, all hand-laid in a style called trencadis. But surely, even on this project, that was going too far.
Basically, trencadis means broken ceramic tiles on together on the same word, right? Anyway, mosaics is good. And I will show you they are 1 square meter panels that came pre-made on a flexible net from Valencia with different numbers. You can see like a wave, a zigzag cut, right? Can't you? And just 1 meter up, there's another one here, right? And there's another one over there. Once you have this information, you can see the different levels of this surface. We have made a jigsaw puzzle here.
Truly, the only word that comes to mind is spectacular. The effect you get when the music plays, something that truly transports you.
Te transporta, ¿no?
Close inspection may reveal a small cheat, but stand back and its full effect is plain to see. It all adds to create a glistening introduction to a music lover's evening. In Scotland, 20 years ago, an audacious plan was hatched to reconnect 2 of Britain's most historic canals. They were only 300 meters apart, but one was 24 meters higher than the other. For waterways that were once the superhighways of the Industrial Revolution, that is worlds apart. But an effort to reconnect these 2 canals overcame the huge problem with an engineering solution of stunning simplicity and efficiency.
This is the only Ferris wheel boat lift in the world.
This is the Falkirk Wheel, a fusion of sculpture and engineering, breathing new life into a historic canal, and now a tourist destination in its own right. The wheel can effortlessly lift nearly 500 tons of water and 2 boats through 24 meters while not spilling a drop or breaking sweat. So how did they build it? 250 years ago, these narrow channels helped transport goods around the country, fueling Britain's booming economy. Here, the beautiful Union Canal runs to Glasgow in one direction, and the Forth and Clyde Canal runs to Edinburgh in the other.
These canals were the lifeblood connecting Edinburgh and Glasgow during the Industrial Revolution. And it also provided a luxury high-speed service, the bullet train of its day.
The waterways were completely reliant on a system of locks, which allowed these 2 canals at different heights to be connected. But by the late 1800s, trains were all the rage, and the canals and crucial lock system between them was barely used.
Due to the height difference between the Forth and Clyde and the Union Canals, 11 locks were needed to get the boats from one to the other. But these fell into disrepair in the 1930s.
Perhaps not surprising when you consider taking a boat through these 11 locks took almost an entire day. Eventually, they were demolished, and the stretch of locks and the waterway between them lay disused. Glasgow and Edinburgh were no longer connected by canal.
It was broken, fractured, you might say, during the 1960s and 70s with roads and other obstacles.
By the mid-1990s, canals were back in fashion, now used for pleasure rather than industry. British Waterways wanted the old route restored. To join the canals, they would have to dig a new canal, but overcoming a massive height difference was more tricky. Rebuilding the hopelessly slow staircase of locks that once connected the two canals at different heights was not an option. So in the mid-1990s, the search for a modern solution began. The design that was given the go-ahead was a completely original concept.
This is the world's first rotating boat lift that can take boats in a circular direction from one canal to the other. What we've created here is a piece of sculpture that becomes a landmark and a destination for Scotland.
The Falkirk wheel is a 200-ton steel Ferris wheel with two gondolas or caissons pivoting around a giant central axle. The caissons act as huge buckets that hold water and the boats. The wheel turns, moving the boats and 500 tons of water to connect them 24 meters above or below to the other canal. At the top, it's all connected by an aqueduct that would have done the Romans proud. And the Romans would prove to be this project's first obstacle. A Roman earth fortification once stood here. Today, all that's left is a grassy hill, but 2,000 years ago it was the most northern border of the Roman Empire.
Where we stand is the UNESCO World Heritage Site, which is the Antonine Wall, and that was built in AD 142. So we had to actually get the canal underneath the Antonine Wall through a tunnel. The tunnel was about 200 meters long, 8-meter diameter, onto the north side of the Antonine Wall, extend it onto an aqueduct, and then onto the Falkirk Wheel.
Digging a 200-meter tunnel under the Antonine Wall was achieved without drama. Building an aqueduct 25 meters high over the basin was a more serious challenge.
If you had been here 20 years ago, what you would have seen is a whole forest of scaffolding. So everything was supported by scaffolding, so it basically takes a small part of the load of the wet concrete as you're pouring it. And as the 4 piers are poured, we get up to the deck itself. That's all supported and all constructed in 4 sections.
No one had built a canal in Scotland for 200 years. That lack of practice initially caused a few more problems.
Inevitably, there were some leaks. Not in the structure, I would have to say, but in actually the earthworks approaching to the viaduct. But over a series of a few weeks or month, we actually plugged all the gaps in the waterproofing of the canal, and then on a go. And to my knowledge, it's never had a problem in the 20 years since it's been open.
With the Forth and Clyde Canal connected through to the aqueduct, the wheel itself could be installed. This system required trapping 250 tons of water in each caisson and moving one up and the other down 24 meters to the basin below. To engineer a structure able to carry 500 tons of water on the end of 2 steel arms while keeping everything steady and under control meant relying on some key laws of physics.
It's like a balanced beam, and that weight really means it's very, very efficient. And the water and the boat balances out. So we had the unique balanced beam idea that I don't think there's another boat lift that uses that principle. It uses other elevator type principles with weights and things, but not a balanced beam, which is the fundamental system here.
The natural balance of having equal amounts of water at each end makes sense if both the caissons have a boat in. But how does the Falkirk wheel stay balanced if it's only transporting one boat and the other is empty? To answer the question, engineers made clever use of the Archimedes principle.
Archimedes had a eureka moment when he realized that if he put an object in his bath, the weight of the object was displaced exactly with the water. And it's the same principle here.
So in this case, as a boat floats into the chamber, it's going to remove the exact amount of water that's equal to the weight of the boat. So that means that as long as you keep the water levels the same, it's going to continue to weigh the same, with or without the boat.
Now, the massive payload needs to be rotated.
Normally, moving 500 tons of water 24 metres in the air takes the same amount of energy as a typical Scottish household over 3 days. But all the Falkirk wheel needs is the equivalent power of 8 boiling kettles.
The balancing act means the wheel is easy to turn. As the wheel lifts one tank, the downward force of the tank on the other side does most of the work. Like a seesaw, water keeps the wheel balanced, but it creates another problem. Each massive tank contains 250,000 litres, and if this water starts sloshing from side to side, there could be trouble.
The biggest problem is the water. You have to keep the gondolas or the tanks level. Plus, when you start to move water, it creates a critical mass that's really hard to stop. The entire structure could tip over if it's not carefully controlled.
We had to solve the problem of how to stop the water from making the caissons turn over. Because as you move them around, they're inherently unstable. You know, if you take a ferry full of water and the water flows from one side to the other, you know, it's very difficult to control it once it starts to move.
The best solution proved to be the simplest.
It's connected by a simple system of cogs and wheels. We have 5 cogs, of which the central one's fixed, and the outer 2 are fixed to the caissons, and then the 2 wheels in between are allowed to freely move around. And what they do is they allow caissons to always remain horizontal no matter what forces are applied to the 2 beams going around.
As the wheel turns, the central axle drives cogs that run up the arms of the wheel. These are geared to create an always correct connection to the caissons, which stops any internal forces affecting their position, prevents the caissons swinging out of control, and keeps them permanently level and safe. The Falkirk wheel is the perfect marriage of beautiful design realized by clever engineering, reconnecting an historic canal route with a uniquely modern solution.
The finished wheel is a piece of pure engineering meets Celtic sculpture, providing a breathtaking example of how human problem solving can achieve the spectacular.
It's still very well attended. It's one of the main tourist attractions in Scotland, and it actually sits as an iconic structure within all the other iconic structures that have been built in the UK and in Scotland. And again, very proud to have been part of the team that actually delivered this.
It's in the British passport. You know, it's on the Scottish pound note. And it's really great that something of today that takes old technology and reuses it in a different way and is innovative in the way it approaches things is actually celebrated. And that, I think that's the best thing of all. You know, if people can enjoy and know that there's a future and there are more things to be discovered, that's the most exciting thing.
How does this incredible skyscraper defy the laws of physics and stay standing?
This house always is on the verge of falling down.
What happens when one of the world's richest men and its most extreme architect create the impossible?
But obviously we know that levitation of buildings hasn't been invented yet.
And how do you build a 300-meter high elevator in an area so remote, heavy machinery can't be used? This is the age of the extraordinary.
Where else can you swim from one skyscraper to the other 300 feet in the air?
Where ingenious engineers have unleashed unchecked creativity.
Everything in this building pushes at the boundaries of what's possible.
Building structures so outrageous, they defy logic.
The forces on this thing look like it should be torn apart.
Now, their secrets revealed. Discovering the incredible stories of their construction.
These are extraordinary feats of engineering.
To try and understand, how did they build that? New York's Manhattan Island, where the skyscraper rules the roost. Ever since the first one went up over a century ago, the drive has been to push towers taller and cheaper. But the resulting demands on engineers have created repetitive, predictable shapes. Creative flair and groundbreaking design were rare exceptions. That was until 2017, when in Manhattan's Tribeca district, a spectacular new tower was unveiled. This is 56 Leonard Street, where a team of engineers and architects stepped over the cutting edge, ripping up the skyscraper rulebook.
The shapes are extraordinary. I mean, boxes stacked on one another, and some of them are slid out. The whole thing looks so precarious.
At Leonard Street, 56 stories of unique apartments are stacked ever more daringly right up to its 250-meter summit. Here at the top, engineering logic seems to have been recalibrated to defy the laws of gravity.
It all just looks a bit scary.
Unique apartments with sky-high, impossible overhangs created a complex and expensive construction. So how did they build it? Even more than most cities, Manhattan is space-hungry, resulting in tall buildings with simple layouts that are a compromise between the engineering challenge of building a skyscraper and the practical economics of doing it at a price.
Most skyscrapers or tall buildings are either rectangular or tubular because those are really efficient shapes when it comes to supporting themselves.
For construction purposes, and developers like to have buildings be fairly regular, columns going straight up, etc., so that every floor is the same and they can just build it nice and quickly.
These uniform layouts are now so efficient to build that a conventional high-rise with over 50 floors can be completed in just weeks. But the results are often a little underwhelming.
Imagine you wanted to change things up a bit.
You could put this cantilever section in there, this box section in there, and you might even want to, like, take out bits. Oops.
Changing it up in the world of skyscraper construction means taking risks. But that wasn't going to stop developer Isaac Senbahar.
We knew this was going to be a very tall structure and very visible from almost every angle in the city. So we said, okay, we have a responsibility to do something iconic. We didn't want something repetitive, some just straight up building. We wanted something more interesting, more sculptured.
When Isaac bought the site in 2008, Tribeca was not one of Manhattan's glamorous residential districts. But building something special anywhere in New York is expensive. So these apartments would have to command top dollar. Needing a design that would attract the uber-rich, Isaac headed to Europe and world-renowned Swiss architects Herzog and de Meuron.
We felt that Isaac was ready for a new approach, a more radical approach.
Herzog and de Meuron's portfolio includes some truly incredible buildings, like Bayern Munich's Arena Stadium and London's Tate Modern Extension. But no skyscrapers.
Even if we had done a building before, a tall building, we would always look at it from a different angle and would give him something unexpected. We wanted to be a stack of apartments, but not an anonymous one. The building could be understood as a pile of individual pieces, even in the middle part, and then the top, which would have even more exclusive apartments, which we decided could become like stacked private homes. And I think that's really new and hadn't been done before anywhere.
There's good reason it's never been done before. In order to make a strong, stable, tall building, irregular spaces are normally built into the super-stable lower floors, with smaller structures at the top. The architect's concept that the higher the apartments are, the more off-balance they appear, flipped conventional high-rise engineering on its head. To pull this trick off at the top, they needed to reduce structural complexity lower down, while still making the floors appear to be different. To do this, they hatched a cunning plan. The first 46 floors would be built in the conventional way, using continuous outer columns and inner walls to provide support for the floors above. The floor layouts would also repeat, but they'd been made to appear different by changing the size and position of balconies and edges. The 46th floor would be unoccupied, and so could be packed with load-bearing walls, creating a 47th floor plate that would be a super strong, super stable platform for the rest of the floors above. Skyscraper specialist Hez Zimena was the engineer tasked with making it happen.
We tried to stiffen up the building enough up to the 46th floor, so when we reach the 47th floor, the first Sky Villa, the building will have sufficient stiffness that we can have the flexibility of doing whatever we want structurally and give the architect the freedom to do whatever he wants with the space.
And what the architects wanted was to create an extraordinary visual effect.
If you make this upper box, let's say, hover to a certain degree, you don't make it hover so it collapses. You can push it to an extreme, you know, like in Chaplin's movie, you know, where this house always is on the verge of falling down. Together with the structural engineer, you find the right moment between something fragile, something even dangerous.
That vision for off-balance apartments that still had wraparound views meant pushing structural concrete engineering right to the edge. The lower floors used conventional skyscraper engineering, where continuous columns share the load. But because the top 9 floors were all offset, that same system wouldn't work. Each of these floors had to be stiff enough to support huge cantilevered overhangs, some over 7 meters. And they had to do that without compromising the view from within. To pull it off, engineers turned to a 125-year-old idea: the Vierendeel truss. A regular truss uses diagonal cross members to create triangles that make it very strong both laterally and vertically. But the views from within would be ruined. A Vierendeel truss connects the 2 floors using only vertical columns, so it's just as strong vertically, And it keeps its lateral strength through the massively strong central lift shaft column that also connects the floors. So the Vierendeel truss allows huge openings, and the apartments above can be offset with crazy overhangs.
A Vierendeel truss is actually a brilliant solution for a long cantilever. They were developed by Alphen Vierendeel, a 19th century Belgian engineer who developed the super strong truss, particularly resistant to bending forces.
The advantage of utilizing a Vierendeel truss is that it's not obstructive architecturally. Like traditional truss would have a diagonal member crossing through the space, and that would be very obstructive architecturally, and it's kind of prohibitive. So we came with a different approach.
So this is how the Vierendeel truss became the key to building the sky villas. On super stable floor 47, concrete columns are precisely placed where they will give support to the floor above. This creates the first Vierendeel truss. The central lift shaft provides all the lateral strength, so the floor remains beautifully open plan, but can still support the tremendous downwards forces from the 8 unique stories built on top. These trusses create such rigidity that the upper floors don't have to sit directly on top of one another, allowing the amazing overhangs. All helping to make the sky villas some of the most spectacular homes in the world.
There's literally nothing underneath us other than the slab, and then it's straight down to the street level, 800 feet below us.
Not only are they over 200 meters up, but at up to 550 square meters, the 9 sky villas are huge, each exclusively occupying its own floor and each with a unique layout. Situated in up-and-coming Midtown Manhattan, it was hoped homes here would fetch sky-high prices.
This is a building aimed at some of the wealthiest people in New York.
The lower apartments up to the 45th floor would be priced between $3 million and $10 million, while the plan was the sky villas would sell for over $20 million. And those hefty price tags were needed, as it became clear the top 9 floors, with their unique layouts, were going to be slow and expensive to build.
You know, you do 3-4 floors of all the same thing, and then you're used to it, then it's just automatic.
But of course, Herzog's 9 sky villas were all unique.
Every floor plate is a different size and shape.
So every floor was kind of, there was a learning curve. And then you learn that, and now it's a new plan. It's just like, you know, the game changed every time we poured.
Because each of the sky villas is different, before work could start on the apartment above, the one below needed to be strong enough to support it. And that meant more time for the concrete to set.
The biggest challenge for the contractor is to hold the forms and the scaffoldings in place until the concrete cures and reach its required strength, and then he can remove the scaffolding and the temporary supports.
You know, in New York, we used to pour 1 floor every other day. Here, some floors took 6 weeks.
By 2014, the lower 46 floors had taken 20 months to complete. And with the top 9 floors set to take 9 more months, extra measures were taken to make the site safe and weatherproof.
It was actually very interesting to see during construction that it had this black curtain protection around the entire 10 floors. Once everything cured, they start stripping down the scaffolding, and then this beautiful structure, it's almost like a sculpture, revealed itself to the public.
So, with patience and engineering ingenuity, the impossible overhanging sky villas had been created. But before anyone moved in, the building needed protection from something that spells trouble for any skyscraper: the wind.
Tall buildings will always move in the wind, and that can't ever be completely stopped, and they'll always move, in some cases, by quite a lot.
New York has recorded winds of up to 100 miles per hour, and Leonard Street's sheer height and comparative isolation from other scrapers means in high winds, it can move by up to a foot at the top. It's engineered to handle this amount of flexing, but left unchecked, these movements can keep on increasing, potentially collapsing the building. So it's crucial there's something to counteract these forces.
A lot of skyscrapers have what's called mass dampers. They're basically counterweights. So for example, if the wind is pushing one way, the counterweight pushes the other way.
Most skyscraper counterweights are large suspended blocks like this. But at Leonard Street, they chose a damper system sometimes used to cope with the ultimate threat to buildings: earthquakes. Skyscrapers in earthquake zones have water tanks to cope with the swaying induced by a massive quake. This is what 56 Leonard Street uses.
At the top is a giant tank of water. When the building moves one way, due to the wind, the water in the tank moves in the opposite direction.
So 56 Leonard Street was ready for the forces of nature. But in 2016, just a year from opening, the engineers needed to get the inside prepared for new residents. To do this, a twist was given to an otherwise ordinary feature: the lobby staircase.
You have a stair, so do the stair in a way that it's nice to walk up and down. It's inviting, I would say, to take the stair, if it's 1, 2, 3 floors perhaps.
As usual at 56 Leonard, the stairs would be made of poured concrete.
So the way to design something in concrete, it's called formwork, and it's really simple. It's basically just creating a mold of whatever shape you want and pouring the concrete in, letting it dry, and there you have it.
Sounds simple. Except when the pour involves nearly 50 tons of concrete, and the architect is demanding a seamless finish for his stairs. A seamless finish is created by not letting the concrete set between pours, so preparations needed to be meticulous.
5 months to plan the stairs and create the mold that the concrete would be poured into.
It started with experts conducting the whole pouring because concrete has air bubbles in it, and that's why they use vibrators. This guy was conducting everybody where to use the vibrator. It was a very, very precise operation and a long day.
The carefully poured staircase was typical of the attention lavished on every inch of this building. Once finished in 2017, the quality of Leonard Street was obvious. But potential buyers had understood this was a special building way before that. Sales had opened in 2013, and almost immediately someone agreed to pay $47 million for a sky villa. A record for any address below Midtown Manhattan, and a sign that the risks taken by its developer would pay off.
I think we broke a record. We sold close to $1 billion in 9 months.
2.5 million man-hours, 27,000 cubic meters of concrete, and 5,000 tons of steel went into creating Leonard Street's 46,000 square meters of space. It had taken over 5 years, but a towering landmark now graced Manhattan's skyline. And if proof of its success was needed, locals have affectionately given 56 a nickname.
Someone spoke of the Jenga tower. At the beginning, I didn't even know what he was talking about. But people like it, and if people like it over a certain time, this is a good sign.
It was difficult, it was 10 years of my life, but to build a building like that in the skyline, it always feels good that, you know, you've built something like that.
56 Leonard is remarkable. I mean, it stretches the limit of what's possible to build, what's structurally possible, and then celebrates that.
"12,000 miles from the man-made towers of Manhattan are Mother Nature's skyscrapers. The towering sandstone columns and miniature rainforests of Zhongjiajie National Park in central China are a unique spectacle on planet Earth.
This is a UNESCO World Heritage Site. Beautiful, yet strange landscape. There's nowhere else like it.
Unsurprisingly, millions of people want to see it. And what's the best way to enjoy that incredible view? By taking the world's tallest outdoor elevator. The 326-meter-high elevator of 100 dragons is better known as the Bailong elevator.
This is the elevator that hangs off the side of a cliff. It's taller than the Eiffel Tower, taller than the Shard in London.
The site was so remote that heavy machines couldn't be used to build it. All the work was done by hand.
It carries 1,380 passengers an hour, and all in the middle of an earthquake zone.
But laser systems and escape tunnels keep the tourists safe from seismic danger.
And if you don't want to take the elevator, you can just go ahead and take the 999 stone steps.
Stepping all over the park is exactly what thousands of people used to do. In the 1990s, word about the stunning landscape spread, and soon huge numbers of curious tourists were tramping through the delicate forests and climbing its fragile rocks. Its ecosystem was suffering. The Chinese government had to act. One of the best views of the park is from this peak. So to keep visitors under control, but still let them see the incredible natural wonder, they built this astonishing elevator. Half inside, half outside, a huge rock face. The visible upper 172 meters is actually only just over half the elevator's total height. The lower 154 meters is hidden in shafts tunneled inside the cliff, and at the bottom of those is a 200-meter access tunnel leading to the main concourse. It all works smoothly now, but its creation was an epic feat of human endeavor and engineering. The first stage was to tunnel into the mountain to where they were going to build the base of the lift shafts. Today, it's used by hordes of visitors to reach the elevators after they've got off their coaches. But when the project was started in 1999, road access was severely limited, and no heavy equipment could be brought in. Liu Qie is manager of the elevator facility.
We used 100% human labor, with no heavy equipment and industrial machines used during construction. Workers carried all the equipment and materials on their shoulders or with their hands to the hillside.
So using only hand tools, the tunnelers got to work.
We first dug a tunnel into the mountain at its foot. Then we drilled the elevator shaft in reverse, from bottom to top.
Yes, you heard correctly. They drilled the shaft upwards. This is called reverse circulation drilling.
Drilling wells from bottom to top is actually very difficult and dangerous, as the wells above the workers can collapse at any time, and yet workers had to keep drilling upward.
With the 154-meter shaft reinforced, the exposed mountainside above needed to be made much more stable and strong before it could take the weight of the elevators.
More than 4,000 rock bolts were inserted up all 326 meters of the mountainside, and anchor cables were connected to the rock bolts so they could surround the mountain.
With the huge column of rock tightly wrapped with steel cables, wire mesh was added and concrete sprayed over the top to create a rock-solid mountainside. Next, the huge steel derricks, or frames, were bolted onto the reinforced cliff face. Finally, the elevator cabs could be installed. Those 3 huge double-decker cabs can each carry a payload of almost 5 tons, or over 50 people. With their high speed of over 5 meters per second and world record 326-meter climb height, they demand state-of-the-art control systems. Computers keep the cabs balanced and smooth in transit. To save power, electrical energy is recovered by the motors as the cabs descend. But perhaps the most important engineering at Bailong are the safety systems. Because the stunning beauty of the Zhongjiajie region hides a deadly threat.
It is an earthquake zone where they've had historically quite significant earthquakes that have killed a large number of people in the vicinity and in the surroundings, and it's something that could happen again.
With the elevators in almost constant use, raising over 20,000 people up to the viewing platform every day of the week, the consequences of a major quake could be catastrophic. So Bailong's engineers have built in every safety feature they could to quake-proof the structure.
We have 7 wire ropes above the cab, and actually every single one of them can hold the weight of the cab. The second safety measure are the guide rails along both sides of the cab. The cab is tightly fitted to these rails and has brakes which will stop the elevator from falling, even if all 7 cables fail. The third safety guard are the 4 hydraulic bumper posts we installed in the elevator pit. This is to soften the impact of the cab if the other safety gear fails to work.
Of course, prior warning of an earthquake would be the best safety feature of them all. Just a few seconds warning could save hundreds of lives here. So a system of lasers is sited on distant hillsides, which train back to receptors mounted onto the steel structure.
The lasers shining across the mountain are extremely sensitive. They can monitor the tiniest of movements in the earth and can notify the control room to perform evacuation procedures.
Just a few millimeters of movement will trigger the alarm, and instantly the elevators will automatically take passengers to one of the evacuation exits, built every 11 meters into the cliff face. But for now, the Earth moves only for those lucky enough to gaze at one of the planet's great natural wonders.
Since 2015, we have experienced an explosive increase in the number of visitors, with about 4.5 million tourists coming here in 2018.
The park is now the second most popular tourist attraction in China, and it's being kept in pristine condition. All thanks to the engineers who figured out how to build this incredible elevator. Paris, France. Carefully planned, very traditional. Famous for its immaculate boulevards and ornate apartment buildings, all combining to create its unique character. No wonder when bold new structures are proposed, it often takes a while before the Parisians appreciate them. In 1889, the Eiffel Tower was described as a truly tragic street lamp. In 1977, the Pompidou Center simply monstrous. And in 2006, a new building joined their ranks.
This building is definitely out there. It's weird. You look at it and you're like, is it a broken perfume bottle? Is it a giant ship? Is it a UFO from outer space?
A building designed by one of the world's greatest architects that locals hated and set out to stop.
In Paris, it's difficult to imagine this kind of building.
Bankrolled by a billionaire, money was not the problem. Figuring out how to build it was.
I think it's fair to say there were some very dark days in the process of putting this building together.
The challenge of creating this astonishing building took hundreds of engineers, architects, and craftsmen, 8 years and 800 million euros to overcome. So how did they do it? When a man worth $100 billion decides he wants a new building for his art collection, he doesn't just buy one off the peg. Instead, in 2006, luxury brand magnate Bernard Arnault got in touch with the man described as perhaps the world's most important architect. 94-year-old Frank Gehry dreamed up Bilbao's Guggenheim Museum and the extraordinary Lou Rouveau Center in Las Vegas. This time, Gehry was inspired by the great glass palaces of the 19th century and designed a building that would set a new benchmark in extreme engineering challenges. The 11,700 square meter building was to be called the Louis Vuitton Foundation Museum. It would include a massive waterfall, 11 galleries, and a 350-seat auditorium. It would have huge steel icebergs and all be shrouded in 12 billowing glass sails. The budget was a cool 130 million euros. Frank Gehry's buildings were already notorious for challenging engineers' abilities to innovate. This building would take that reputation to the next level. James Cowie spent a decade of his life working it out.
This was not a smooth ride down the river, as we say. Myself and the engineers went to Los Angeles to meet with Gehry Partners as they proudly showed us their model of the building, what they intended to build. And they did a very, very long exposition. And they finished by saying, well, what do you think? And the structural engineer next to me thought for a second and then said, I think you used a lot of glue to make your model stand together.
Gehry's glue-happy model makers had good reason not to confront the question of how to build it. The design's sheer originality meant there was no structural template to follow. Nothing to suggest it was actually possible. But Cowie's team took a logical approach to planning the build.
It's a very tricky and complex building, geometrically, obviously, when you see it from the outside. You could break it down to 4 basic systems that put the building together.
The engineers devised a solution that was based on illusion. The huge glass sails appear to be supported by the small curving structures known as the icebergs. A signature of Frank Gehry designs, they look like the core of the building, but they're not. Melt away the icebergs and some very conventional concrete cubes emerge, within which are the gallery spaces themselves. Now these are not very Gehry, but they are very solid and allow the building's outer skin of sails to be so extreme.
They give the appearance as if these sails are floating in the air unsupported, but obviously we know that levitation of buildings hasn't been invented yet.
But to appear to levitate, the flimsy glass sails would still need many more smaller fixings, because of course, being sails, strong wind was a big concern. The forces of gravity and wind on a building would normally be calculated by computer models. But so much was unknown about these ultra-complex structures that computer modeling wasn't trusted. Getting the plan right meant going back to basics.
We built a mini building, which was not more than 50 square meters on the ground. We have all of the systems, the sails, the glass enclosure, the icebergs, and we did a test run in which we evacuated many of the problems that we would have been confronted with if we had built without doing this test.
The successful dry run gave the builders the green light. By 2011, the project had been underway for over 5 years. But as the foundations and central concrete structures began to appear, protests about the size of the building and its impact on the park intensified.
A group of Paris residents challenged, they didn't like it. They challenged the original construction permit.
A court order found the building contravened Parisian planning laws. The huge project was stopped in its tracks.
When we were asked to suspend construction, we were quite in the middle of things. And so we had to keep working for another 2 or 3 months just to stabilize the building so work could be suspended because it was in a bit of a precarious state.
With 1/3 of all the scaffolding in France on site, Gary, Arnaud, and the hundreds of specialists involved found their dream in the hands of the courts. But Bernard Arnault fought back. The court battle ended 4 months later, when the city of Paris suddenly changed its laws on land usage. Frank Gehry was back in business. While the foundations and concrete cubes were taking shape, the components that would create the steel icebergs and glass sails were being made off-site, a long way from Paris. Gehry's mixed use of material was typical and challenging. Arcing beams of wood and steel support impossibly complex glass panels, many exposed to the elements. Making these to the highest standards meant using only the very best workshops and craftsmen. Engineer Bernard Vaudeville helped coordinate the massive Europe-wide project.
All the elements are prefabricated. They are made in workshops, which are 100 kilometers away from Paris. For the glass, it's made in Italy, and the wood was made in Germany, and some other elements were made in Belgium. So all these elements had to come from far away, and they were all prefabricated.
More than 400 specialist fabricators in 4 different countries would create the 23,000 unique pieces that must somehow all fit together perfectly when assembled on site.
That's basically the jigsaw puzzle from hell.
So how did they make sure it would all slot together? The designers used a system created for a different, but even more demanding industry.
The designers used technology pioneered by the aviation industry. It's called BIM, Building Information Model. It lets all of the manufacturers add information to a 3D model and then lets the designers check what everyone is doing.
This shared virtual building model meant teams on-site and off-site were all fully aware of any problems arising and could rapidly agree solutions, dodging time-consuming meetings and expensive mistakes.
Basically, this model was the base on which everything was created, and it allowed for the contractors in different parts of the world to fabricate pieces of amazing geometrical complexity.
First of the prefabricated structures to be assembled on site were the icebergs.
We're here in the iceberg, the highest one. These shells were prefabricated in Belgium and were transported to the site, to Paris, on trucks, trailers, and assembled, as you can see, with bolts, simply bolts, with joints that you can see here. All of these shells were different. There were 365 different shells for all the icebergs of the project. It was assembled on site to compose the external shell of the iceberg.
Now the iceberg shells needed to be clad with a huge number of custom-made white tiles, which all had to be just the right size before they arrived.
Normally, it doesn't matter if you have to adjust things on site. I mean, that's part of the building process. But you can't really do that if everything is so custom-made.
Instead, Bernard's team relied on components being made to within a few millimeters of specification, so they weren't too close or far apart once assembled.
Assembling them on site is very difficult because there is something we call tolerances. Tolerances means that when you fabricate something, it's never exact, never. You can't do that. Exactitude is only divine. It doesn't exist.
On top of all this complexity, because every tile is different, each one had to be attached in precisely the right order.
You have 19,000 of these white panels. Almost all are different.
So they came in boxes. When you open the box, the panels had to be in the right order. You can't open 50 boxes in order to find where the good panel is.
With the icebergs complete, next came the huge sails. With 13,000 square meters of curving glass, these were perhaps the most challenging features of all to create.
3,500 panels of glass, with each one with an individual design, for which special ovens had to be created to manage the curve, to manage the way the surface would be treated to reflect or not reflect light.
Commercial car windscreen making combined with meticulous hand craftsmanship to ensure each panel curved precisely the right way and was safe to install.
There were multiple constraints just on the glass that required us to work with glass manufacturers to invent a whole new way of fabricating glass.
Finally, in 2014, 8 years after it began, and with nearly 800 million euros spent, the Louis Vuitton Foundation Museum was ready to hold its first exhibition. But for many, the art inside was a sideshow. Because Frank Gehry, his architects, engineers, and craftsmen had achieved something extraordinary.
The thing that I really love about this building is that the structure is on display. So many buildings, the structure, the actual bits that hold up the weight in the floors, it's just not visible. It's behind walls, it's behind cladding, you never see it. But with this structure, you can really see the columns, the frame, the skin. And to me, that's really inspiring.
Beautiful, but the work that went into it was extraordinary.
Against what had once seemed impossible odds, Paris had a new icon on its skyline, to match perhaps even that famous Tower of Steel itself. What happens when the world's most radical architect tries to revive a 100-year-old building?
This project obviously stands and falls with structure. I mean, this is a structural masterpiece.
How is one of the world's tallest residential skyscrapers even standing?
columns are what make a building stand up. You take away that structural support and
how do you create a building that would have been impossible just 10 years ago?
Building in water is incredibly difficult. I mean, you've got to hold back an entire river while you're building.
This is the age of the extraordinary.
This house always is on the verge of falling down.
Where ingenious engineers have unleashed unchecked creativity.
Everything in this building pushes at the boundaries of what's possible.
Building structures so outrageous, they defy logic.
The forces on this thing look like it should be torn apart.
Now their secrets are revealed, discovering the incredible stories of their construction.
These are extraordinary feats of engineering.
To try and understand, how did they build that? Ever-growing cities are in a constant battle for space, risking demolishing the old to make way for the new. But in Antwerp, Belgium, one of Europe's busiest ports, a forgotten 100-year-old building has been transformed beyond imagination. A groundbreaking architect has turned this historic firehouse into a landing pad for an extension that is truly out of this world. Challenging engineers to float the new addition effortlessly above the original building.
It leans forwards, it's backwards, it's completely off-center on the legs.
Manufacturing the entire structure off-site and then shipping it in massive 400-ton pieces.
We're dealing with making sure we protect this precious building that lies underneath.
Breathing new life into every inch of its new home. This is the Antwerp Port House. So, how did they build it? The Antwerp Port Authority, the government body that controls the busy port, needed a new home. They decided on a long-forgotten firehouse in the center of the industrial complex. It needed some serious work if it was going to function as their new headquarters. But they didn't want to demolish the original listed building.
Adding to existing historical structures is a real challenge. You've got the technical challenge of being able to work around and load and repair what can be quite old and historic material of the building. But then you've also got the aesthetic and the kind of heritage issues as well. You need to build something that's going to be true to the original history and aesthetic of the structure, or complement it in quite a stark and interesting way.
They brought in one of the world's most famous architects, Zaha Hadid, to come up with a solution. Her visionary designs, like the Gwangju Opera House, were known for pushing engineering to the limits. This would be her last project, completed before her untimely death in 2016. Joris Pauwels would oversee the project on the ground.
This is maybe the biggest and most prominent existing building we've taken on to develop into a new overall project. And it's definitely a challenge, but it's something that we relish. It gives all kinds of new perspectives on how to deal with existing fabric, urban fabric.
They had to figure out how to build a futuristic extension to create extra space to house new offices, while protecting a beautiful historic building that would form the rest of the Port Authority's new headquarters.
The original design had 4 equal facades, meaning there's no front entrance. 4 facades were equally important. So we definitely wanted to preserve that quality of the existing building by building a volume on top and not blocking visually one of the main facades.
The architects also wanted to preserve the building's central courtyard. Conservation specialist Philippe Lemonnier was charged with protecting this piece of Antwerp's past making sure the radical design didn't destroy the building or rob it of its original identity.
We can see in the typology of a fire station there's a lot of elements. One you can see on the right side is that there are a lot of gates for fire trucks, and then you have the backside in the middle of the facade, the dry tower. Those elements are very important for a fire station.
Studying the plans for the firehouse gave the architects an idea, one that would honor the original design and let them build something out of this world. It turns out, the building was never actually finished.
It was built in 1921, and the original design of the fire station had a big tower on top, which is twice the size of the building, very extravagant. It was never built, and which made us consider an extension on top of the existing building as a kind of contemporary endpoint to the existing building.
This monumental extension not only brings the building into the 21st century, it completes the vision of the original architect. The plan was to build a precision-engineered, futuristic extension over 20 meters above the historic building to house new offices, supporting the 1,500-ton structure with two massive concrete legs, and to join the new extension to the firehouse through the old tower where the firemen used to hang their hoses to dry. The engineers got to work figuring out how to support the massive steel structure above the 100-year-old building without damaging it.
This project obviously stands and falls with structure. I mean, this is a structural masterpiece. We'd like our buildings to float if we can. So we definitely try to minimize the points and keep this idea of a large hovering volume over the existing building. The new building cantilevers out over the square in front of the existing building. It's quite a dramatic effect pointing towards the city center of Antwerp. The structure of the new building is a steel structure. It's held by two concrete pillars.
The engineers built the two concrete legs to hold up the new offices, with the front leg designed to wildly lean out. It looked dramatic, but without precise calculations, risked dropping the brand new building on top of the firehouse.
Because the front leg is leaning out at an angle, it's going to want to push out at the top and slip under the building at the bottom.
They decided to connect the front and back legs at the top and bottom, turning the structure into a massive concrete ring, with the bottom part of that ring underground.
By connecting these two legs at the top, they are kept from falling out of the top, and at the bottom, stopped from slipping in.
The two pillars are obviously not vertical, so we have a very dramatically inclined front pillar, which needs the concrete ring to keep it from falling over the square. So that's why this ring is very important as a structural element.
The ring is joined just under the massive steel and glass structure, and the bottom connects 3 stories underground in the car park, keeping the legs in place and letting them support the weight of the extension. The top section stops the giant concrete leg from falling over, and the bottom stops it sliding out from under the massive steel structure. Then the whole thing is steadied by another 4 interconnected steel supports. The engineers did all this whilst barely touching the old firehouse.
We try to keep the impact on the existing building very minimal, and that is equally important when we created this structural ring, which goes through the foundation work of the existing building. So it's a very minimal connection, both structurally, where we connect the foundations, as well as physically, where we introduced a small staircase leading up to the entrance hall inside the existing building. We've got a 2-story underground car parking, so it's 2 stories down. Underneath that, so at the 3rd basement level, if you like, that's where we made the connection between the foundation of that inclined front pillar and the central pillar which rests in the courtyard.
What did the conservation specialist think of this radical approach? Did it do justice to the original building?
The opportunity to do the second feet at the inside of the building in the courtyard. But we still needed to have the aspect of a courtyard. You can fill it up with feet and structure, then you have no more courtyard and you have no more lights inside. You can use even more this space. So the engineer and Zaharit tried to find a way that you could have this structure, but with a kind of subtlety that these are sculptural elements in the inside. And so you can see that those elements even not touch the old structure, just landing inside the building, and they make possible that this big volume above our heads is standing over there.
With the gigantic concrete legs in place, the engineers were ready to tackle the futuristic glass structure. But constructing it was going to be a bigger undertaking than anyone had imagined.
Having the new building floating in midair, it's important that that's not a super heavy construction, so it's a steel structure. It also is a sustainable structure, so we looked at a whole number of possibilities of constructing the building. We did a lot of analysis with the contractor to see how they could build platforms, how they could get enough people up there.
To preserve the original building and realize the precise design, the engineers decided to build almost all of the new extension in a factory 90 kilometers away.
It was clear after an initial analysis that building the steel structure off-site in big modules, shipping them to site and installing them was a much faster and more economical way of constructing the building.
Normally with steel structures, you build upwards with scaffolding support and welding as you go. But in this case, they were building over the existing structure. You're looking at a lot of scaffolding support with all the risks of building over and around this listed precious building. So what do? You build it 90 kilometers away in 400-ton pieces and ship it in.
So building the structure of the new building off-site in factory means it's much more controlled in terms of tolerances, making sure everything is completely right. They even installed a temporary structure to ship the modules on boats to the location. And then all they had to do is lift them in place, so it's a much faster construction procedure to build the overall volume. The structure of the new building is built in 6 separate steel parts, 2 steel pieces per level, and they were lifted in place and then assembled on top of the existing building.
The 100-meter long, 60-meter high, and 20-meter wide steel structure was broken up into 6 enormous 400-ton pieces and shipped from the factory 90 kilometers away on massive barges. The builders used a remote-controlled dolly system to offload these giant sections.
So it's both light construction, it's a lightweight construction time, which is important, and also the kind of environmental concern that we had. So this is achieved by having this steel structure made off-site and coming on-site by boat.
The scale of this job is immense. Just look at the size of the platforms that are used to drive off the sections from the barges. They're each the size of a truck. It just seems mad that this is the safest and quickest and most efficient way of working. But it just illustrates that to make a building like this, you really have to approach it from a completely different way of thinking.
With the steel megastructure in place, they turned their attention to the building's signature glass facade.
We wanted the glass volume to maximize views out, maximum light coming into the office environment. And what we looked at is to create a dynamic over the length of the facade, as if this building is in motion. And we did that by playing with faceted triangles that go from a flat facade on the south side to a completely faceted pineapple structure on the north side. So this transition makes that when you observe the building from distance, it seems to be in constant flux with light, with clouds, with sunlight playing on the triangles. It seems to be a kind of moving object over this static classical building.
The finished effect means the glass is constantly changing as you walk around it. There's something of the effect of the glittering sea or fishy scales.
The gigantic extension was secure, glistening above the old firehouse. But there was still no physical connection between the two structures. How do you connect two massive buildings with the least impact possible? They decided to use the firehouse's old dry tower.
You do an extension to a building. At one place or at one moment, the two parts have a place where they meet together. What we see is maybe the only physical touch between old and new is the dry tower. When we see the dry tower, we see a little bit of masonry above the roof. And then we see a start of a glazed elevator shaft. The elevator starts in the old dry tower, go to the glazed shaft, and then enter in the new building.
Although you enter the lifts at the bottom of the existing building in the tower, the lifts take you up to the new building and connect. But the structure of these lifts is hung independently from the steel structure of the new building. So it's not actually touching the brickwork of the existing tower. The existing brickwork tower acts as a sleeve in which the steel structure is hung independently from the brickwork, completely loose from each other.
The amazing thing is that both of these buildings are separate. Replace the bricks, and good as new. Of course, that would be a very expensive change of heart.
The radical new extension was in place, transforming the original fire station, seamlessly combining groundbreaking architecture with a sense of history to bring a forgotten firehouse into the 21st century.
I think actually that our project allowed this building to be reinstated as an important landmark within the Antwerp urban fabric. There might have been all kinds of other scenarios where this building would have been demolished and something new would have been built. And I think it was very important also for Zaha herself to keep this existing building, to stay with this and to have a separate layer coming over it, to layer the city instead of demolishing and rebuilding.
We have a larger building with a bigger capacity, working 500 people in it now. And we have also a remarkable site now here, a site maybe forgotten in the past.
What we have here is a building that deeply respects the original and gives it space. Yet it also reacts against it with something so crazy and outlandish. The overall effect is that we have these two structures that exist together, but have their own identity.
Deep in the heart of New York's Manhattan Island, one of the most prestigious addresses in the city has a new resident. An 88-story skyscraper, one of the highest residential towers in the world. It's classed as a super tall.
There's only about 146 of them in the world.
It's really become a club that people are desperate to be a part of.
Not just tall in the extreme. At just 28 meters across, it's also very slim and vulnerable to the city's wild winds.
432 Park Avenue is 15 times higher than the width at its base.
To create luxury apartments with unspoiled views, the engineers had to do away with internal columns. The project would cost $1.25 billion and push skyscraper engineering to its limits. This gravity-defying wonder is 432 Park Avenue. So how did they build it? It's 2011, and on a small plot in Manhattan, an ambitious plan is being put into action. To build a 28-meter wide tower, 426 meters into the sky. Dimensions never seen before in skyscraper engineering. Engineer Hetzi Mena was tasked with figuring out how to build this developer's dream.
It's not a normal, typical building. It's very tall, small footprint, it's very slender. There's a lot of challenges. It's a tremendous effort put in for over 5 years from start to finish.
This super tall, super slim design was difficult enough to build as it was. But there was another curveball coming the engineers' way. With apartments needing to fetch $75 million plus, no one wanted internal columns getting in the way of luxury interiors. They told the engineers to get rid of them.
Taking away columns is all well and good, but unfortunately they're very important for holding up the structure. If you take them away, then you need an alternative way to carry those loads down to the ground.
Columns are what make a building stand up. You take away that structural support and...
With a building this tall, you need a way to hold up the weight of 88 floors. Normally, this is done with internal columns. Without them, they needed a way to support this super tall skyscraper.
So like a typical 20, 30-story building would have a central core, what we call the backbone of the building, and that will hold the wind and the earthquake, seismic, horizontal forces.
This is the backbone of the building. It's what gives buildings their strength.
For 432 Park Avenue, at 88 stories high, that wasn't enough. The engineers decided to make the building's outer shell super strong to reinforce the structure.
This building has a backbone, which is also the central core, but we also supplemented the exterior columns, so together they are providing the stability that the building needs.
They inserted supersized steel rebar into the concrete outer shell for added strength.
To make concrete stronger, you put steel reinforcement into it.
And in this case, it's a gigantic piece of steel.
Architects Chuck Knapp and Gloria Glass kept a section of this super thick rebar as a souvenir.
You can see the size and the diameter. These are major rebar. And
in general, they're this size, you know, right?
Right. And the deformations on the side of the bar are normally not this. This is screwed because they need to be able to screw these into couplers. So it's a different animal, but it's pretty big. And this thing is only about an inch, inch and a half, and it's very, very heavy.
It wasn't enough, though, just to have a super strong facade.
It had to be tied to the core of the building, that area that houses the elevator shaft.
This supersized rebar made the outside of the skyscraper incredibly strong, but the engineers made it even stronger, connecting it with steel beams to the concrete elevator shaft, which acts like a spine running down the length of the building. The skyscraper's core and reinforced exterior gave it the strength to tower 426 meters in the air. But this height made it vulnerable to New York's infamous winds.
A skyscraper is a structure that people live in. You hang out there, you sleep there, and if the architects and engineers don't do anything about the wind, then you're really going to feel it, especially if the building's thin.
All structures that we build move. But in tall structures, they're particularly prone to being moved by the wind. And the thinner the structure, the more vulnerable they are.
The skyscraper was vulnerable to turbulence created by the wind. If the wind was strong enough, it could make the building shake, making it uninhabitable and even risking damage to the structure.
When you have a tall, thin structure like this, and when the wind strikes it, the wind then wants to pass around the building, creating turbulence on the backside. That turbulence creates vortices, swirls of wind which pass up the full height of the building. And the turbulence creates the swirls to first be on one side, and then the other, and then the other. This is called vortex shedding, and what it does is it starts to actually buffet the building sideways, even though you're blowing it straight on. Now, any building has a natural frequency. Think about pushing a child on a swing. If you push the child at the right frequency, the child will start to go higher. Same thing happens to a building. If these vortices start to form and push the building at the right or the wrong frequency, then the vibrations will start to get out of control.
The engineers started to take out windows, letting the wind rush through floors that contain the skyscraper's pumps and other utilities.
So we found that when you make these penetrations in the building at certain locations, it reduces the wind pressures by about 20 to 25%.
Every 12th floor is open to the air. That lets the wind blow through. Really clever, but it doesn't solve the problem completely.
To make sure the skyscraper could even survive New York's strongest winds, the engineers had another trick up their sleeves. The masterstroke, the brilliant engineering trick, is hidden away at the very top of the tower on the 84th floor. Two secret giant machines that directly counteract the wind.
The wind acting on the building wants to make it sway. To stop that happening, then they've used tuned mass dampers, which means a huge lump of concrete high up in the building. It's an active system, which means that when the building wants to sway in one direction, the hydraulic jacks will move that lump of concrete in the other direction, counteracting that force and hopefully keeping the building not moving too much.
This particular building, we have a damper, weighs about 1,300 tons, absorbing the energy of the wind that exerts on the building. So it has to be fast enough so the occupant that sits in the apartment doesn't feel the movement of the building.
Which is good news if you've paid over $75 million for one of the incredible apartments.
432 is without a doubt a feat of world-class engineering. It cost a staggering $1.25 billion to build, and by my estimation, it's about as beautiful as a skyscraper can get.
.432 Park Avenue towers above the competition, giving one of the most sought-after addresses in New York its best view as well, using clever engineering to take skyscrapers to their limits. On the rugged east coast of Scotland, a shipbuilding powerhouse had fallen quiet. But all of that was about to change thanks to one extraordinary structure. The brainchild of one of the world's most radical architects. The Victoria and Albert Museum in Dundee rises from the River Tay, forming a man-made cliff. This revolutionary design forced engineers to construct a huge dam in the middle of a raging river. Build a gravity-defying 8,000 square meter shell in one piece of concrete without a column in sight. And hang 3-ton slabs off impossible walls.
It looks like the forces of this building should just completely rip it apart.
So how did they build it? In Dundee, Scotland, the city's industrial heart needed a kickstart. The radical plan was to build Scotland's first design museum in the historic shipyards where Scott and Shackleton's legendary Antarctic ship had been built.
It's been very important in this project to have a remarkable building. This is a new design museum, so it seemed right to look for an ambitious design that would inspire people to come and see the building. A building by an architect who was so brilliant at responding to a particular place, about the relationship between the river and the city.
Visionary Japanese architect Kengo Kuma designed this brutalist masterpiece. He used Scotland's stunning landscape for inspiration.
The opening island, we found a beautiful cliff. Reminds me the spirit of Scotland, because it's very tough, and the nature is very tough, but still the cliff is fighting with the tough natures. Reminds me the history of Scotland and the culture of Scotland.
The plan? To lay the foundations in the middle of the Tay River, whilst battling the Scottish weather and protecting local wildlife. To cast a giant concrete shell that uses nothing but its own strangely shaped walls for support. And hang the signature cladding with pieces weighing up to 3 tons from the gravity-defying walls. Their first task was to lay the foundations, but this wasn't going to be easy. The design called for a huge portion of the building to stick out into the Tay.
There are serious issues with building in water.
Building in water is incredibly difficult. I mean, you've got to hold back an entire river while you're building.
How do you lay foundations in the middle of a river? Structural engineer Dan Clipsome had to tackle this monumental task.
Building in the water isn't fundamentally different from building on the ground. The foundations of the building still need to go down to bedrock. So whether it's in the river or on the land behind the river wall, we're still piling down 20 meters into the rock to get a good foundation for the building. Dundee is a very nice sunny city most of the time. It's also cold and wet in winter, like many places. So the weather plays quite a key part in construction. We're working by a tidal river, working in a climate that has extreme cold during the winter, and rain and wind. They all need to be considered during construction.
They had to lay the foundations on a seriously difficult site. To make it possible, they decided to build a dam out of 12,500 tons of stone and earth, called a cofferdam.
A cofferdam is an enclosure built within a body of water to allow the enclosed area to be pumped out.
That means that you can get on with your work in a nice, dry environment.
The cofferdam would let the engineers extend the existing dockside, pushing the site into the Tay. Building the dam was a race against time.
There are protected species in the river, particularly a species of seal, and so we had a very short time scale that would allow us to build our foundation out in the river. We went on site in March in 2015, and we had to make sure that all of that work that was done out in the river was done by the beginning of June, the beginning of the seal pupping season.
The local grey seal population lives close to the site. Their breeding season was just around the corner. And the second it started, all work in the river would have to stop. They'd have to work quickly. The construction team hammered massive steel slats into the riverbed, filling in the center with rubble to hold back the force of the Tay River.
What was done in this case was a temporary bit of land was created. So the contractor installed a piled wall out into the river and filled it in with ground to create a new bit of land that we could then build the building on. We were constructing the building on top of solid ground, even though it was above the river.
The engineers drilled down 20 meters, anchoring the building's foundations to the bedrock on concrete piles. At the same time, they had to make sure the corrosive salt of the Tay wouldn't eat away the foundations. They decided to use a concrete with a special formula, specifically designed to resist salt.
Salt and chlorides are the enemy of our structure. So they cause corrosion and damage to the building over time that we have to prevent. The concrete mixes we've used in this building had to be different. We had to change them from what we'd normally do in order to make them more resistant to the elements, to the salts, to all of the things that are trying to attack the building.
The foundations were secure, and a new piece of land had been built into the Tay River, ready for the next step of the build. The engineers now had to tackle the building's radical shape. They wanted the walls to support the entire structure, removing any interior columns from the gallery spaces. But the leaning and twisting design threatened to tear the museum apart.
Normally, you would never build walls that are sloping outwards, and that's because as well as the usual gravitational forces that are pushing down on the building, you're adding an extra layer of strain as the walls are being pulled apart.
The shape of this building is really incredible, and something that you don't see in architecture very often for a reason, and that's because it just takes a lot of expertise, science and maths to achieve what they've achieved here.
To get the calculations right, they used the very latest 3D computer modeling and sculptural techniques.
This is a building that is a very modern design. We needed to use a lot of computational power to create the design of this building. We looked at the shape at the concept stage, and we could have put a frame in here and hung the facade off the outside of it. It could have been a traditional building. The problem with that is we'd fill the building with a lot of stuff. And this is a museum, this is an art space, this is a gallery, this is a place for people to come and enjoy that we didn't want to fill with bits of steel and concrete. Historically, we'd build buildings with the walls carrying the weight. Stone huts back in the Dark Ages. The walls carried the roof, and that was how you protected you from the wind and the rain. So we took the option of using the shell of the building as its structure, kind of going back to the old way of doing things, make the outside of the building hold the building up, and then you don't need to put anything inside. Because of the way the building is pulling on all the different bits of itself, the roof pulls on the walls pull on the roof, we had to design it as one big object.
To make the most of the exhibition spaces, the architect didn't want any interior columns. To achieve this, the shell of the building, the exterior walls, had to support the roof and themselves. No easy task given their extreme shapes. The solution was to design the shell to work as one piece, using its own weight and steel reinforcements to hold the building together. But there was a problem. The shell would only be structurally sound when the last piece was in place. Until then, the whole building was unstable.
So the leaning walls and the whole building is really held together by these tension forces, pulling everything back towards that central core.
The skin of the building itself is doing all the work. It's carrying the weight of the building, it's pushing and pulling with different forces, it's resisting the wind and the rain, it's keeping the building watertight, holding the facade up and the cladding on the outside, but it's primarily supporting the building.
They used their advanced computer model to make the walls super efficient, making them as thin as possible and, more importantly, light.
That resulted in some of the walls being half as thick. They went from 600 millimeters down to 300 millimeters, which is a significant saving in materials and reduces the weight of the building, the size of the foundations. You know, there's a lot of positive outcomes from that.
Now they faced the challenge of building the 2,300 cubic meter shell. This would only be stable when the last pour of concrete had hardened. It wouldn't be able to support its own weight until the very end.
Because of the shell we had to make, it was like casting a giant mold. We had to finish the casting before we could take the mold away, because in a partially completed state, the building isn't stable.
As the shell started to go up, the builders had to add more and more formwork, the molds that hold the concrete, to support the precarious structure. If they removed a piece too early, the whole structure would collapse. After a year and a half of constant work, the last concrete pour was completed. It was time to take off the formwork and see if all the calculations were correct, and this one-of-a-kind design would support itself.
Finally, after nearly 2 years of it coming into place, it came down. And it was a very, very exciting moment to see that formwork removed and the shell of V&A Dundee finally born, finally revealed.
When the molds were removed, the black concrete underneath was revealed, colorized with PFA paint or pulverized fuel ash made from the waste of coal-fired power stations. At last, the V&A's groundbreaking shell was complete. But architect Kengo Kuma wasn't going to leave it there. He had big plans for the finish.
Instead of vertical wall, we tried to bring that kind of pure natural formation to the building.
He wanted to use giant concrete blocks to mimic the craggy appearance of Scottish coastal cliffs. But it turns out creating a random natural pattern is harder than you think.
If you look at the facade of the building, at the external panels from outside, you'll see that they all look slightly different. There's a random pattern to them. They step in and out, they step up and down, they kind of weave around and create this sort of vision of this cliff face, of this random assortment. In reality, they're not that random. If we did an entirely random pattern for the facade, if every plank was just generated by some mathematical formula, the risk is that 2 or 3 planks next to each other would look similar enough that your brain would see them as the same. So we had to create this algorithm that allowed us to fine-tune things to make sure the architects could look at the building from every angle and they could tweak and adjust until it looked just so.
With the shell working as one piece, it was ready to take the massive weight of all the cladding. All in all, there are 2,500 pre-cast rough stone panels, weighing up to 3,000 kilograms each and spanning up to 4 meters. Hanging them was going to be a challenge.
The facade panels are made from a concrete and reconstituted stone material. They weigh an awful lot. The facade, the panels, weigh about the same as the wall that's holding them up. Panels on a more vertical wall are smaller, panels on a more sloping wall are bigger. That presents another challenge because the walls that are sloping and twisting are working harder and the cladding hung off them is heavier. So it's a sort of double whammy of challenge that we had to overcome in the design.
The anchoring points of the giant stone cladding had to be seriously heavy duty. The engineers decided to set them in the shell when it was first being poured, letting the outer shell harden around them. This, though, left no room for error. Get it wrong, and the cladding wouldn't fit on the shell. In the end, every anchor, bar 3, was in the perfect position. The exterior of the building was complete, a testament to the Scottish landscape. The V&A Dundee is proof that radical engineering can breathe new life into a long-neglected area, using the natural environment to redefine the urban landscape.
The end result is a beautiful building that is truly built to last, as tough and rugged and as beautiful as the Scottish landscape that inspired it.
Dundee is falling in love with its waterfront again, and people that come to experience V&A Dundee now have a new relationship with the river, which has been such an important part of this city.
Extraordinary engineering challenges had been overcome to create the designer's vision.
I consider this to be a landmark project. I find it fascinating that people look at it as a piece of engineering as well as a piece of art and architecture. It's a visible piece of structural engineering.